Hello everyone, welcome to this video. Today we are going to start off with another topic, the second organic chapter you have in your class 11 syllabus, that is hydrocarbons. General organic chemistry is actually going to pave the way for learning hydrocarbons. We have already understood what is general organic chemistry and we have finished that chapter, right? The video is still on our channel. If you haven't watched it, go and watch it. It's an 8 hours long video. So today in this video we are going to take up the chapter hydrocarbons. Now some things like isomers, this will again come in hydrocarbon, but that part I won't be telling you in this lecture. Why? Because isomers well and nicely has been told in the GOC lecture, so that I won't be taking up now. Okay, so let's begin the lecture without any further delay. We are going to start with the very fundamental of hydrocarbons, that is the basic classification of hydrocarbon. So if I talk about hydrocarbon classification, how is hydrocarbon classified, then what will be your answer? Hydrocarbon means compounds which are going to contain carbon and oxygen, that much as carbon and hydrogen, that you already know, that is hydrocarbon. Now based on some parameters we have classified hydrocarbons into certain divisions. So what are the division? What is the basic fundamental division of hydrocarbon? Hydrocarbon is saturated, unsaturated, that is the second division. But what is the first and the foremost division? That is going to be whether it is a straight chain compound or it is going to be a cyclic compound. So the first division that has been done is alicyclic or cyclic. Understood? Alicyclic or cyclic. Alicyclic means the first and the last carbon, they won't be connected. The first carbon and the last carbon, they won't be connected, right? And in cyclic, it will be the first carbon will be connected with the last carbon. The moment the first carbon touches the last carbon, it becomes a cyclic compound. Clear? So one is alicyclic, another one is a cyclic compound. Cyclic. Now the second division under alicyclic is your saturated and unsaturated. So saturated and unsaturated. So let's write that. Saturated, unsaturated. Now saturated, we have only 1% which is sitting under saturated, is your alkane. So saturated has only one thing, alkane. But unsaturated further having two divisions, that is alkene or alkyne or alkyne. What does saturated mean? Saturated means those alicyclic hydrocarbons which have only and only single bond present in them. They are the saturated ones. And the unsaturated ones are, they will have double bond or triple bond. That means they will have multiple bonds present. So they can be broken down into alkanes. Clear? Right? So that is an alkene and that's an alkyne. Now under cyclic, we have two types of cyclic compound. One is a normal cyclic, another one is a little bit different type of cyclic. That means one cyclic says, ah, I'm a normal cyclic. Another one will say, no, I am a very special kind of cyclic. So I will be called as aromatic cyclic compounds. Clear? So we are having normal ones, that is cycloalkane, and we are having aromatic compounds. We will be reading about benzene. Aromatic compound. Cycloalkane, nomenclature part is generally asked from cycloalkane, and which we have discussed in the GOC part. So in this chapter we will be discussing about the aromatic cyclic compound, primarily benzene. Right? Benzene you all know, that is the most important thing. So we will be discussing about benzene in this chapter. Done. So first we will begin with which topic? Which topic? We will begin with obviously the simplest compound, the saturated compound. That's an alkane. So we are going to begin with alkanes now. Before I start with anything of alkane, you have already read about alkane in class 10. So what exactly is alkane? The very simple ones, the fundamental ones, comprising only and only of single bond. Those are alkanes. So what do we need to know about alkanes first? We need to know about alkanes general formula. Though general formula question was asked in class 10. But now it will not be asked, but you need to know what is the general formula of alkane. So what exactly is the general formula of alkane? Alkane is a homologous series, right? So a homologous series must have some common formula, right? That common formula is the general formula. So what is the general formula for alkane? The general formula for alkane is CnH2n plus 2, right? This is the general formula which the alkane group follows. N is the number of carbon atom, while if you multiply it by 2 and add 2 to it, you will get the number of hydrogen. So this is the alkane. The simplest possible alkane is methane, right? The first member is methane. This type of question was asked in class 10. First member of this homologous series is CH4, that is called methane according to IUPAC rules. Clear or not clear? So these are the basic fundamentals. Now as and when you increase the number of carbon, you will be talking about isomers and all that, right? What are the isomers possible for butane? Isomers possible for butane? Is it possible for butane? Yes, it is possible for butane, isobutane. Only one, and normal one, two isones. If I'm talking about pentane, then I will get three types of isomers that I will get for neopentane, isopentane, and n-pentane. These are the isomeric topics which I have discussed in your first lecture. So that I am not going to discuss right now. Clear? Okay. Now let's come to the next topic. Let us see what is the next topic. We have preparation of alkene. Alkane. Now you see, alkane we need to prepare, right? How will you prepare alkane? That we have to study in class 11 in details. In class 10 you have learned about this basic things. First member, general formula, simple reactions of alkane like oxidation ones, then simple reaction of alkane we have learned in class 10 like the substitution ones. Now in class 11 also we are going to discuss that, but we are going to go into a little bit more depth. So let us begin with the first reaction, that is called the Woods reaction. Woods reaction we have already done in class 10. If you remember, what was Woods reaction? Class 10 you did Woods reaction, right? So Woods reaction is the best method to prepare alkanes. Okay, I will not say best, but like it's good one, right? So what exactly happens in a Woods reaction? You do not have to memorize the reaction. What you will do is you will not memorize the reaction. Simple. You will not memorize the reaction. You will remember the basic syntax of the reaction. That means how the reaction goes, not the mechanism. I'm not talking about the mechanism. I'm talking about the one formula. You will just know that this way the reaction can occur. So basically, if you find a reaction, first I'm giving you an example of a reaction. From there I'm deriving the syntax. Okay. Acha. See here. Let us take CH3Cl. Okay. 2 times CH3Cl I'm taking, and I'm reacting it with Woods to undergo Woods reaction Na to Na, and I am going to give it with dry ether. Acha. If you have attended your school classes, then you must have known that even in the name reaction and the conversion, you have to put it in a balanced format, right? So I have to use 2Na and 2CH3Cl. It's not like you're writing CH3Cl and you're using Na. No, you have to balance the equation. Clear? So 2CH3Cl, 2Na, dry ether. If I am going to do this reaction, then the reaction will be giving me CH3, and it will give it to me 2NaCl. This is going to be the reaction. Okay. Another reaction let us take. Suppose I am writing 2CH5Br and I am reacting with 2Na in presence of dry ether. Then I am getting C2H5 plus 2NaBr. Now how many reactions like this will you memorize? Number of carbon is not defined. Many carbon, whatever compound can come. Then what will you do in that case? You will keep on memorizing. And for this is this, for that is that. No, you are not going to memorize. What you are going to do is you are going to simply prepare a general formula. See here. Achha, you all know that R represents alkyl group in organic chemistry. Wherever you find an R there, R is an alkyl group. This will not be mentioned again and again. R is an alkyl group. So whenever I write R, you have to understand it's an alkyl group. Whenever I write an X, you have to understand that I am talking about the haloalkanes. That is a halogen group. Clear? These two things you need to remember. That whenever I am writing about X, you have to understand that it is an halogen group. When I am talking about an R, you have to understand that it's an alkyl group. These are the two things which you need to remember, because each and every time it will not be mentioned in the paper that this is this, this is that. Clear? You have to understand it on the question. Understood or not understood? Any doubt? So these are the two things which you need to remember. Now let us understand that why is the reaction so. Sorry. See here. CH3 is the R group. Is it or is it not? CH3 is the R group over here. This CH3 is the R group. Can I say that CH3 is the R group over here? Right. So can I write 2RX because this is the X group and this is the R group, this is R and this is X. So can I write 2RX? I can write, right? No doubt. So I am writing 2RX in place of this, right? Reagent will not change. Reagent will remain 2Na in presence of dry ether. Reagent will not change. And please, reagent you have to memorize. That you cannot forget. No. Whenever Woods reaction coming, the reagent is 2Na and dry ether. Clear? Now come till here. Here this is also an R. This is also an R. So can I write R bonded R? You can see from there, no? R bonded R. So I am writing R bonded R. Right? And this is 2NaCl. So then I can write 2NaX. Right? So this is the general formula which you need to remember for Woods reaction. Not these two reactions you will memorize. You will remember only the general formula. Clear? The general formula for the reaction is 2RX 2Na RR plus 2NaX. This is the general formula which you are going to remember. Clear? I am just shifting it a little bit below. I am rubbing the upper example. Clear? Do you understand which you have to remember? You have to remember the general formula. The general formula will help you to solve the reactions based on Woods reaction. Right? Now here also we will find this is R, this is X, R, R and X. Done? So all the examples will be following this general rule. So this is going to be an example of Woods reaction. Clear? Simple questions will be coming from Woods reaction. Now questions won't be asked like 265B and that. So this is going to be a very easy question. Now it may be asked, depends on the teacher, right? Not on me. But the usual type of question that will be asked is based on conversion. Based on conversion they will give you. Like they can give you, I'm just showing you a easy one. Ethane to butane. How will you convert? Use Woods reaction. You will get ethane to butane. This type of questions can come. Okay. If it is asked convert methane to ethane, then how will you convert? Directly like this you will convert. These are all going to follow the Woods reaction. So this type of easy questions can come from Woods reaction. Understood? Clear? Now, ethane to butane will not only involve Woods reaction. Why? Because we are not converting one alkane to another alkane. If you see clearly, we are having one halide, this alkyl halide. This will be said as an alkyl halide. Okay, this will be said as an alkyl halide. Alkyl halide. Okay, so we are converting alkyl halides to alkanes. But there in the question I have given ethane to butane. That means this side also alkane, that side also alkane. Now you cannot convert alkane to alkane directly. Then you have to first do alkane to alkyl halide. That will involve another type of reaction that I will be teaching a little bit later. Clear? That is called substitution reaction. First you have to substitute it, then you have to get it. Clear? Directly you are using Woods reaction for ethane, it is not possible because you will not get the X part. What will you write for Na? Just Na. That will not stay only. Na is very reactive, you know that already. Clear? So Woods reaction, understood or not understood? Understood, I hope. Any doubt about this? I don't think so. Clear with this? Can we proceed to our next topic? Okay, fine. Let's proceed to our next topic. What we have next? Decarboxylation reaction. Next topic we have is decarboxylation reaction. Now you tell me, what does carboxy mean? Carboxy, here carbon. Okay, carboxy, here carbon. Actually carboxylic group, no. That you have to remove. Carboxylic group you are removing. Okay. D means something removed. Both in biology and chemistry, D means removal. So D removed. What you are removing? Carboxylic group. Clear? So you are removing a carboxylic group, you are degrading the number of carbons, you are decreasing the number of carbons. So reactions where you have to decrease the number of carbon, you will be using this reaction, decarboxylation reaction. Clear? So the first and foremost important thing that you need to note down from here is that you have to this reaction is used when the number of carbon is to be reduced. When I'm going to do some questions, then you can understand that what does this mean. But when the number of carbon you have to reduce, when you have to reduce the number of carbon, in that case you can use this decarboxylation reaction. Clear or not clear? So when you have to reduce the number of carbons, you are going to use decarboxylation reaction. Now what exactly is decarboxylation reaction? Let us understand that. So as I have already told you, carboxylation is carboxyl group and D means removal. So D remove, that means remove the carboxyl group. So if you remove the carboxyl group, it is decarboxylation reaction. Then how it is done is basically, you see, you have a CH3 plus CH2CONA. This is sodium acetate. When I am reacting sodium acetate with sodium hydroxide in presence of calcium hydroxide, I will get the product as methane and sodium carbonate. Now you have to balance the reaction. So you will use a 2 over here, you will use a 2 over here. So oxygen will be 2, 3, 2, then CH4 to CH3CONA, 2C done, oxygen 2 plus 2, 4 done. Okay, so CH3 CONA plus NaOH CO CH4 plus Na2CO3. This is the reaction that you are going to do. This is called decarboxylation. That means you have to lower the number of carbons. What you have to do? You have to lower the number of carbons in this case. So what is the basic funda of the reaction? The basic funda of the reaction is, okay, so basic funda is that you have to write RCOO plus NaOH in presence of CaO to give the RH plus Na2CO3. Clear? This is the basic funda. So these two will not be there. The reaction is already balanced. Clear? So RCONA plus NaOH will give in presence of CaO RH plus Na2CO3. So this H is not visible. H. RH plus Na2CO3. Clear? And this is the example of this reaction. Basic funda is this one and this is the example. Okay, please remember the basic funda because that will be only required in your exam. Acha, NaOH plus CO is called soda lime. So soda lime is also you have to remember. NaOH plus CO combinedly we will call it as soda lime. So this is soda lime reaction as well. Some cases you might find they are saying soda lime reaction. What is soda lime reaction? Nothing but this NaOH plus CO is only called soda lime. So this will be a soda lime reaction as well. Clear with this or not clear? So basic funda is RCONA will react with NaOH to form CO RH plus Na2CO3. When are you going to use this type of questions? This equation you are going to use this equation. Suppose the equation is around your let's take your equation is, let's take ethanoic acid. You have ethanoic acid. Okay, you are going to convert it to methane. Then you have to use this decarboxylation, not directly. I am repeatedly saying not directly, because this directly you cannot do. No, ethanoic acid is not there only. Then what you have to do? You have to use one extra step. What is that one extra step? Nothing. You have to bring it that Na. No. So you have to do something that the Na is getting substituted inside it. That's all. That's all you have to do. That's all you have to do. And I'm showing you how to do. If you are having doubt, just a minute, I'll show you. Ethanoic acid to methane, or you will suppose propanoic acid to ethane. This way. Clear? These were actually class 10 questions. If you remember, this were class 10 class it was given. Right? Then now how to go from this to this? We get a empty slide. Now how to go to RCONA? It's very simple. Suppose you have RCOH, right? If you treat it with NaOH, what will happen? Na will get replaced by this H, no? Then so it will simply be RCONA plus H2O. Done. Well and very simple reaction. So ethanoic acid to methane will be first ethanoic acid going to acetate, sodium acetate. After that only you can do it. Directly though you cannot do it. La. Did you understand this? Simple. Clear or not clear? So first you have to go, you have to do this step, then you have to show that step, right? Suppose the question, let me do one question. Ethanoic acid to, in exam it will come as convert ethanoic acid to methane. Then what will you do? You will directly write this reaction. You will directly write this reaction. No. If you directly write this reaction, it's wrong. You have to show the step. So what you have to do is, first you have to show CH3 COOH. You are converting that to acetate first. That you have to show that CH3 CONA I have done, and water I have to write the byproduct, because byproduct missing marks 0. You all know that. CH3CONA. Now I can do decarboxylation. So this NaOH CO. The moment I do that, I will get methane plus I will get Na2CO3. Bicarbonate you have to write, otherwise gone. So you have to write this step. You have to write this step. First step, you have to show that hydrogen is getting replaced by sodium. That you have to show, otherwise it's wrong. Clear with this concept? Any doubt about decarboxylation reaction? Any doubt about decarboxylation reaction? So we have learned about two methods of preparation of alkanes. One is Woods reaction. Second one is decarboxylation reaction. I hope no doubts about this till now. Fine? Okay. Next we are going to see what is the next topic we have. Let's see. Grignard reagent. Now we are going to discuss Grignard reagent. These are all the methods of preparation of alkane. The third method of preparation of alkane is Grignard reagent. What is that? Grignard reagent is an organometallic compound. What is an organometallic compound? That will be an organic compound that will be having a metal inside. It is an organometallic compound. So Grignard reagent is an organometallic compound. So first thing I will be noting it down for is Grignard reagent is an organometallic compound. An organometallic compound. What does that word organometallic compound mean? Organometallic compound means that there is a metal bounded to an organic compound. Clear? Now let us discuss what exactly is organometallic compound, or what exactly is Grignard reagent rather. Okay. Grignard reagent, basically it has three fundas for Grignard reagent. Okay. Example I am coming a little bit later. First you have to prepare the Grignard reagent, then you have to do the reaction, right? Directly, so it will not be giving an alkane. First you have to make the Grignard reagent, then you have to do the reaction. So how will you prepare the Grignard reagent? You have to treat the given compound in presence of Mg and dry ether. Mg and dry ether you have to react that compound with, then you will get it. Okay. So suppose it's an Rx. Rx means R. What is R? You already know. What is Rx? X also you already know. So Rx, if I treat that in presence of magnesium and dry ether. For Wood's reaction it was sodium dry ether. Here it is magnesium dry ether. Then what the compound I will get is RMgX. And this RMgX is known as Grignard reagent. This RMgX is known as Grignard reagent. Did you understand? That first step you have to prepare the Grignard reagent. So this Grignard reagent is first prepared by using this step. Rx, you have to react in presence of Mg and dry ether to give you RMgX. That is, this is the Grignard reagent. Now come to number 2. What will you do? Using this Grignard reagent, now you will be preparing the compound, right? RMgX plus water. Usually we give you water. Now instead of water, it can be alcohol as well. That I will show you, whether it is alcohol or whether it is water. The product will be alkane. One product will be alkane. The byproduct will keep on changing depending on what you are using, whether you are using an alcohol or whether you are using something else. Okay, I am showing for water. For alcohol, the byproduct will be changed. So RMgX plus H2O forms RH plus MgOH X, and this is the required alkane. So required alkane we have got. Clear? So RMgX, when you are reacting with it water, you are getting RH plus MgOH, and that is the required product. Now let us come to examples. Example. Okay. Suppose we have ethyl bromide. What do we have? Ethyl bromide, C2H5Br. This is ethyl bromide. we have to convert this to ethane, ethyl bromide to ethane. So what we will do, ethyl bromide, first we will react it with Mg and dry ether to do what? To get C2H5 MgBr. Now this MgBr we will be further reacting it with water to get C2H6 plus MgOHBr. Now the question can be twisted. How? What format? The question can be twisted in another format, that is, suppose instead of this it is given, let's take it is given C2H5OH. Then what will you do? This byproduct won't change. This product will not change. C2H6 only will be formed. But what about the Mg part? That will change. So instead of OBr, here it will come MgOC2H5Br. OC2H5Br. Clear? Water dissociates as H plus and OH minus. So H plus taken, OH minus gone. C2H5 dissociates as C2H5O minus plus H plus. So H plus taken and water gone. From acids, organic acids, you take the H plus, right? So the remaining part will be going like that. So it will be C2H5O minus, that is going over there, is OC2H5 plus H plus. So H plus taken. So it will be MgOC2H5Br. One question came in the unit test 2 this time, and that was mistake. Many of them wrote OH minus, so it is not OH minus. It will not be like OH minus will go and it will form different thing over there. No, OH minus won't be taken down. Clear? What many of you will do is C2H5 OH will think this part will go out. So C2H5 one hand will get open. So C2H5 and C2H5. This way it will be combining. No, it will not form C2H5 double with C2H5 to form butane. No, it cannot form higher alkane. It is not a step-up reaction, only how it will form higher alkane. Clear? Understood? So this is all about Grignard reagent you need to learn, and you need to practice the basic funda of the reaction. But first you are going to react with Mg diether. Second step you are going to react with either alcohol or water, whatever is given in the question, and you will be forming the product, the major product or the main product, that is known as alkane, and another product, byproduct will be formed. It's very important to write, and the correct byproduct will give you marks, otherwise gone. Then can we move on to the next topic? Okay, let's move on to the next topic. Let's see what we have next. Kolbe's electrolytic method. Next we have Kolbe's electrolytic method. Acha, you have learned electrolysis in class 10. Electrolysis class 10 we have seen that there are two set of reactions occurring. One is occurring in the cathode, one is occurring in the anode, right? They are giving some products to us. Now in Kolbe's electrolytic method, which is an organic compound, so that also will be reacting in the same way. Whatever compound, it's chemistry, so they will be reacting in the same way, right? So organic compound we will take, in case of Kolbe electrolytic method, we will take RCONA, sodium salt. Clear? We will take sodium salt or potassium salt. What we will take? Sodium salt or potassium salt in this case. So you have to make this first of all. Then again the same step as I have shown you in case of carboxylic acid, this case, that you have to first react it with NH to form RCONA. That acetate part you have to form. So here also in Kolbe's electrolytic you have to form the first, you have to form the acetic part, then you have to conduct Kolbe's electrolytic method. Clear? So RCONA written 2 times I will take. Why 2 times I will take? As I am telling you, but we will take 2 times. Okay. Then what we will do? This is an electrolytic method, so we will conduct electrolysis. So we will conduct electrolysis. Electrolysis done. After electrolysis, we will write R written. What are the byproducts? These are the main products. The byproducts are very important over here. Byproducts. First byproduct will be carbon dioxide, 2CO2. How it is coming, I am showing you. 2CO2 byproduct. Another byproduct will be hydrogen. Another byproduct will be NaOH. 2NaOH. Clear? So this is the basic funda of electrolysis of Kolbe. Kolbe electrolysis. Clear or not clear? Basic funda of Kolbe electrolysis clear? Basic funda of cold electrolysis clear, everyone? What is the basic funda? This is the basic funda of cold electrolysis, where you are giving 2RCONA, it will undergo electrolysis to give you R alkane, 2 CO2, H2 and 2 NaOH. Done. Now, what observation can you make from here? Come back to decarboxylation reaction. There also we are using RCONA. There we are getting RH. And we are finding that there is a decrease in the number of carbon. Right or wrong? There is a decrease in the number of carbon. You check decrease in the number of carbon. That's why we are using decarboxylation reaction, right? But if you find here in case of Kolbe electrolytic method, there is no decrease in the number of carbon. Very important question. Sometimes we will be getting confused. Like sodium propanoate, if you make it undergo decarboxylation, it will give you ethane. But if you take it for Kolbe, it will give you propane, not ethane. Right? This is the thing that you need to remember. Okay? This will not degrade the number of carbon, but that will degrade the number of carbon. Right? Understood? Any doubt? Right. Now let's move on to the mechanism. Just I will talk about cathode anode, nothing else. Acha, tell me RCONA, whatever will be the R, how will it dissociate as? Definitely CO minus Na plus, right? So first let's take one example, so it will be better for us to understand that how exactly things are working. Example, let us take 2CH3 CONA, sodium acetate, electrolysis, CH3 plus 2CO2 plus H2 plus 2NaOH. Clear? Okay. Now let's check what exactly is happening. Cathode anode must be. Before that, tell me who is dissociating as what extent? If I talk about CH3COONA, how does it decompose? It decomposes as, sorry, not decompose, or dissociate rather. Dissociate. How does it dissociate? CH3CO minus plus Na plus must be. Right? Now, when you are using this, there must be water as one solvent. Water must be there as well, because you are not taking a solid, right? You have to take a aqueous solution. So you have to understand that water will be definitely as a reactant. Though I have not mentioned it, but water will be a reactant. If you see, the balancing is also not proper. See, this side 6 and that side it is 6 plus for 10. So balancing is not proper. Then what is wrong with the balancing? Because water this side I have not mentioned, as well the balancing is not coming proper. This side is 4 oxygen plus 2 6 oxygen, and this side it is 2 plus 4 6 oxygen this side, 4 oxygen this side. So 2 more must be there. So I have to write 1 hydrogen over there. 2 water I have to write. The 2 water I have not mentioned. But you have to know that water is also one solvent. In electrolysis of Kolbe, water is also playing a role. So should I write water? Yes, I should write water. Okay, so let's introduce water as well, so that there is no error in the balancing. Let us pull it a little bit down. So I am writing the water over here. Plus 2H2. Clear? Now you see the balancing is correct or not. 2 hydrogen, 4 hydrogen this side, and R, some R will be there that I am not taking. 4 hydrogen, 2 and 2, 4 hydrogen done. Water, oxygen 2, 2, 2, 2, 2, 4, 2, 2, 4 to 6. 6 oxygen, 2 plus 2, 4. Correct? Now balancing is clear. That is now correct. So this is the reason you have to understand that where to write what. Now in electrolysis you have already done in class 10. Na? Without water, how will you conduct in electrolysis? Everywhere water is there. Even concentrated also little bit water is there. It's not like completely concentrated, right? Okay. So water has been introduced also here, but here 2 water. Done. Now let us write the dissociation. CH3CONA dissociates as CH3COO minus plus Na plus, no doubt, and water also will dissociate. How? Water dissociates as H plus plus OH minus. Now according to your knowledge of class 10, Who should go at the cathode? Sodium plus or hydrogen? Definitely hydrogen, because whoever is below in the electrochemical series, their standard reduction potential is more. This thing you will be learning in electrochemistry in class 12. I think class 10 you have learned in the electrochemical series only. So hydrogen will go there. So hydrogen will go and accept how many electron? One electron. And it will form what? Hydrogen. Atomic hydrogen cannot react, so it will be for combining with another hydrogen to form a dihydrogen, and this will go out. So here is the dihydrogen that comes out from the cathode. So where is the other chromi? At the anode, obviously. So at the anode we have CH3CO minus going. It will lose one electron. It will form CH3COO. Again, this cannot exist. So this will form CH3COO free dot. This will form CH3 plus CO2 and CO2. How many CO2? 2 CO2. So 2 CO2. Clear or not clear? See, very clear. CH3 bonding with CH3. And how many molecules of CO2 are there? 2 molecules. So that 2 molecules of CO2 gone out. Clear? Clear. Very good. Next. Sir, here to no product came. Right? Here, no NaOH to came. Nowhere NaOH being formed. Where did the NaOH come from in the Kolbe-Electrolytic method? Where? In the syntax of this reaction, where did the NaOH come from when there is no NaOH in the cathode anode? Where? It will not come and suddenly be dropped inside, right? It should come from somewhere. Where? Use your brain. We had one Na plus as well in the equation. This one. We had this person. They also were in the reaction, but they did not form at the cathode and anode. Where did they go? Disappear in the equation. Cannot happen. Right, in the vessel they cannot get disappeared. And where they will go? They will be getting settled at the bottom. Now Na plus here on one side, OH minus on one side. Can this ever happen? No. Then what they will combine to form? NaOH. That is the thing. Na plus and OH minus is left over in the vessel at the bottom, and that cannot stay different. Like Na plus on one side, OH minus on one side. They will not form any compound. Yes, they will form NaOH, and that's where the NaOH is formed. It will be settling at the bottom of the electrolytic vessel. Clear? So Na, let me write this. Settles at the bottom of vessel, electrolytic vessel, as NaOH. Clear? So NaOH will not be formed at the cathode or anode. It will be due to the Na plus and OH minus ions not taking part in the reaction. Clear? Understood? So this is all about Kolbe-Electrolytic method for preparation of alkanes. So let me summarize again. Kolbe-Electrolytic method, for alkane you are going to use an acetate salt, right? That can be any acetate salt. Here I have used CH3. There can be maybe C2H5 and higher, anything. Clear? So it will be resulting you in the formation of RR plus 2 CO2. My R depends on whatever you have taken before, plus 2 CO2 plus hydrogen plus 2 sodium hydroxide. The balancing is important because marks will go if you don't balance. Acha, clear with this? Kolbe-Electrolytic method clear? Next topic, let's see what we have. Next topic we have is some other methods. These methods generally come as conversion type question. Here to conversion you have understood what type of question they will ask you. Where you will find they are asking no step up step down, then you can think of using Kolbe. But again that depends on the question, what is the question asking. The rest of that you will be taking what to do and what not to do. Grignard reagent, you can see you are generally using the halide ones, the alkyl halide to the same carbon alkane. If you are going to convert, you can use Grignard reagent. Okay. Now coming to some other methods, like in some type of questions you will get propantrione to directly some alkane, propantrione to, let us take propane, like this type of things. And what to do? Suddenly from one ketone I am coming to alkane, suddenly from one carboxylic acid I am coming to alkane. This type of things can only be done by some other methods, because here you see ketone or carboxylic acid, none of them are dealing with that. Clear? Only carbon decarboxylation is dealing with that COH group, nothing else. Wood reaction is not dealing with that only. They are all alkyl halide group. But what about if we have some Kolbe Kolbe I'm saying, if we have some ketone or if we have some aldehyde, then can that not be formed to alkane? Obviously they can be formed. For that we must have some method, and that method, some other type of method, is reduction with red phosphorus in presence of hydrogen iodide. Clear? Or hydroiodic acid. Let's understand that what is that. Some other methods. Number one method is if you want to convert from alcohol to an alkane. Alcohol to an alkane. Now, alcohol to an alkane, the simplest method is use red phosphorus in presence of hydrogen iodide, ROH plus HI, or ROH we are using directly, let's write ROH in presence of red phosphorus, hydrogen iodide, heat, then directly we'll get RH, and along with that we will be forming I2, along with that we will be forming H2. Directly we'll be getting this product, so this alkane is directly I've got. So you have to remember this is direct formation for alcohol to alkane. You have to use red phosphorus along with hydrogen iodide. Clear? Now I2 is there, so I have to write 2 over here also. Then balancing done, 2H, then 3H, hydrogen done, balancing done, separate 2H. Now after alcohol I can also have aldehyde. Then aldehyde, what will I do? Then aldehyde also I will be using the same thing, but this will be RCHO. So RCHO in presence of red phosphorus and hydrogen iodide, heat will give you RH. RH, can it give RH? Think logically. Here, where is the H coming from? H is coming from this part. Coming from that part? No, alcohol does not give H. Alcohol gives directly OH. In presence of this, R and H is this hydrogen iodide over here. Clear? So hydrogen iodide and this went gone. Khatam. Now, leftover part was OH, and here leftover part forming with O. So that is gone with H2O. Done. Another hydrogen was there. Done. Now here RCHO, if I take R and H, then I will be left with something else, OCH. What is that OCH? That I cannot take. Then I have to take something called RCH and H. It will be RCH3. So this will form RCH3. 2 hydrogen from here and 1 from here. CH3, RCH3 plus I2 plus H2O. Clear? This will be formed. Now let us take the balancing one also. 2 hydrogen, 3 hydrogen, 3 hydrogen, done. 3 plus 2, 5 hydrogen. So this reaction is clear. Okay, please balance the equation. Okay, I am not balancing it because I have to tell a lot of things about next step also. Okay, please balance the reaction. If any case I miss out balancing, please balance the reaction. Okay, because I may miss out because I have to tell a lot of things now. Okay, next one is ketone. If it is RC double bond O and R, then in presence of red phosphorus and 4 hydrogen iodide, then you will get it as RC H2R. 2 hydrogen enter from here plus I2 plus water. Please balance the reaction. Okay. So you are getting 3 ways: from alcohol, from aldehyde, from ketone. All reagent is red phosphorus and hydrogen iodide. If you are going to form it, then you are going to get alkane, but alkane of higher orders, right? Alcohol to same order, then little bit order increased. You can see. Clear? Understood or not understood? This is some other methods of preparation of alkanes. So please, very important for you to remember this, especially this product, because this is different for all the case. So please remember this. Clear? Then next let us see what we have. Physical property. Physical property, I don't have to say a lot about physical property, that you can directly read from the book. But why I have written this topic is just to say one important thing from this part, that is state chain has more boiling point. This question is very important because they will directly ask you that which one has main boiling point, more boiling point, neopentane or n-pentane. Then in that case you will not know only what to write. So straight chain has more BP. BP is boiling point than branched chain. Why? Because of less van der Waals force. Because of less van der Waals force. Van der Waals force, you know, organic compound, they are going to act. Van der Waals force plays an important role. So due to less van der Waals force, straight chain has more BP than this. Clear? Clear? This is the only thing you have to read from the physical properties of alkane. That is why I have mentioned you here. Okay. Next we will be moving on to what topic? Obviously physical done. Next will be chemical properties of alkanes. Chemical properties of alkanes. Alkanes will chemically do some reactions that we are going to study in this part, chemical properties of alkane. The first sort of reaction that we'll be studying under chemical properties of alkane is substitution reaction. Now, from the name of substitution reaction, you can understand that something will be getting substituted. That is why the name substitution has been given. So something will be substituted. What is that something? Hydrogen will be substituted by some other atom. Right? That is substitution reaction, and this is a characteristic property of only and only alkanes, because no other thing can give substitution reaction. Clear? So characteristic property of alkane, the differentiation test which you will do for alkanes and alkenes, that will be primarily based on substitution reaction. Okay, so this will be characteristic to alkanes. Please remember that this is only characteristic to alkanes, right? Because alkenes or alkynes, they won't give you substitution reaction, they will give addition reaction. Okay, clear? Now what exactly is substitution reaction? Basic funda is, if I am taking a R, let's take RH, okay, and this is an alkane, RH is going to be an alkane, and when I am reacting an alkane with a halogen, halogen will be always in the form of X2. So when I do it in presence of energy, or you can say diffuse sunlight, H nu is energy, or you can write diffuse sunlight, then what happens is one hydrogen of this alkane will get replaced. One hydrogen of the alkane will get replaced, and you will get Rx plus HX as one compound. This reaction will not get terminated over here. It will go on continuing until the last carbon, until the last hydrogen available is replaced by this. Clear? Until the last hydrogen that is available will get replaced by this X, the reaction will continue. Okay, so I am just putting an arrow and I am putting a question mark because I don't know how much carbon is present here. So did you understand why did I put a question mark? I put a question mark because the reaction is supposed to continue till the hydrogen is not replaced. Okay, so this is the basic funda of this. Did you understand? Did you all understand? Any doubt? No doubt. Right. Now next example. Obviously I will give an example, otherwise you will not understand. So example for this. Let us take up the simplest one, methane. So methane plus Cl2 in presence of H nu will form CH3Cl plus HCl. Again the reaction keeps on continuing, and this CH3Cl will get converted to CaCl2 plus HCl, and the reaction continues. CH2Cl2 will get converted to CaCl3 plus HCl, and ultimately it will give you to the final product CCl4 plus HCl. Clear? So you can see the reaction is not ending. The reaction will continue because hydrogen is available. Now, sometimes you will find small questions like this one. This is called chloroform. This can be asked. Chloroform. Chloroform is CHCl3, not CH3Cl. Often you all write CH3Cl as chloroform, but that is not chloroform. CH3Cl is not chloroform. CHCl is chloroform. Okay, that's a point. That's the point. CHCl is chloroform. Done. Now, when we are going to do this, we will not use certain things. What are that certain things? When I am going to talk about this X, this what can this X be? This X can be Cl slash Br only. Why Cl slash Br? F we cannot use due to highly explosive nature. I am writing over here at this side. Okay, please take a note of that. Note number 1, F cannot be used due to explosive nature. F cannot be used due to explosive nature. And number 2 is that iodine you cannot use. Iodine you cannot use. Iodine, it makes reaction reversible. It makes reaction reversible. It makes reaction reversible. I will make reaction reversible. Now who is making the reaction reversible? I exactly is not making the reaction, but HI formation is making the reaction reversible. Now let us take up a next page, and there I am writing. Do we have a page available? I think at the end we have one page. Right. Just take up the page. So we cannot use iodine. Why? Let me write here. Iodine is not used. Reason. Reason, let's understand. The reaction is CH4 plus I2 forms CH3I plus HI. Now, in chemical equilibrium, you must have read that there is a reaction HI breaking down into H2 plus I2, right or wrong? So HI makes the reaction reversible because HI will readily decompose into H2 plus I2. So if HI is getting again decomposed to I2, then what was the use of me doing this reaction? So this will tend to make this reaction reversible in nature. Clear? So if the reaction gets reversible, then that's not my job, right? We don't want to make the reaction reversible. So that is the reason we cannot use this. So I am mentioning it over here. This makes the reaction reversible. This makes the reaction reversible. So if the reaction turns reversible, then it is not good for us. So what we have to do is we have to remove the HI. So that HI is causing the problem. So I have to remove HI. So how can I remove HI? I will remove HI by using HNO3 or HiO3. So to remove HI, use HNO3 slash HNO3 or HiO3. So what is the reaction? Reaction is HI. When HI reacts with HNO3, what happens is the formation is of I2, iodine gas, water and NO2. And when HI reacts with HiO3, and then NO2 will not come, then simply I2 and water will come. So I have to remove this hydrogen iodide because that is my disturbing element. So please remember, this is an important thing, that HI is going to make the reaction reversible. So I will not use iodine because that HI is formed by using iodine. So to remove HI again I am using another reagent. So I am getting double Khatni. That double Khatni I will not do. If we can do in one step, then why will use double Khatni? So which things we will use? We will use only Cl and Br. We are not going to use F and I. F is explosive and HI will make the reaction reversible. Done. Now this reaction proceeds by which mechanism? This reaction proceeds by free radical mechanism. So please note down, reaction proceeds by free radical mechanism. Reaction proceeds through free radical mechanism. What is free radical mechanism? For that you have to watch the GOC lecture. Okay, free radical mechanism. Free radical mechanism has been discussed in details in the GOC lecture. If you don't know free radical mechanism, please go and watch the previous lecture. It is a GOC lecture. It has been discussed in details at the end of the lecture. Okay. So please remember that substitution reaction proceeds through free radical mechanism only. Very important thing to remember. Clear? Substitution reaction done. What is the next topic? Let's see. Next topic, we have oxidation. Now oxidation is very basic one. In class 10 you have learned oxidation of methane and ethane. So the same reaction I will telling you right now also. If I have CH4 and I react with O2, any hydrocarbon reacting with oxygen gives you carbon dioxide and water, right? So CH4 with this will give you CO2 plus water. Done, right? 2 hydrogen, then you have to multiply with 2, 2 2s are 4. Done. So similarly, if I use higher alkane, then higher alkane will give me higher things, right? So I'm not showing for higher alkane, I'm showing for only methane case. Now, this is the normal case when normally if you burn it in atmosphere, then you will get this case. Now, if I give it less oxygen, I give it less oxygen or I do not burn it completely, then what will I get? Incomplete combustion is also a factor and very less oxygen is also a factor. Then what? If I do it CH4 plus O2, and here O2 is a limited one, limited number, limited amount of O2, limited air. There is incomplete combustion. If I do, then I am not going to get this, I am going to get this. Clear? So in this case you see hydrogen I have to multiply by 2, so 2 plus 1 3, so I have to write 3 by 2. So 3 by 2 limited. Just a minute, put it a little bit below. If I burn this in limited air, then I am going to get this. Clear? Carbon monoxide. That is why you should not burn coal in a closed room, because carbon monoxide is poisonous for our health. You know that? Right. Last thing is, if we are using the same reagent and the same oxygen but very less, what we are using? Very less. Very less. Then I will directly get carbon soot. What will I get? Directly I will get carbon soot. This is soot, carbon soot. Clear? Carbon soot, deposits of carbon. Directly I will get very less oxygen. If I give, then I will directly get carbon soot plus hydrogen. Done. So these are the three reactions which you need to remember for oxidation. Now next we have cracking or pyrolysis. Same words, same meaning. Cracking means breaking down one alkane to one or smaller alkanes, or alkenes even it can happen. Clear? So it is at a very high temperature. So write down, cracking or pyrolysis is at high temperature, breakdown of alkene, breakdown of alkane into smaller, not greater, smaller, that means smaller carbon wala alkane, so into smaller alkanes and alkenes. Alkene can also form, okay? It's not only alkanes will form. Here alkenes can also form. So at high temperature, breakdown of alkane into smaller alkanes and alkenes will be called as cracking or pyrolysis. Done? Understood? Clear? So you have to remember that the word high temperature is important over here, because this occurs only during the high temperatures. Not at any temperature you will feel like it's happening. No, it will occur at higher temperature only. So remember the word high temperature, because that is important for here. High temperature, breakdown of alkane into smaller alkanes, and alkene is called cracking or pyrolysis. The high temperature is about nearly what to say, 800-900 Kelvin. So you can understand it's a very huge one. Okay, 800 Kelvin, around 800 Kelvin you take. So let's give you one example only, because this reaction is generally not asked. That's another thing, let me tell you first. This reaction also follows free radical mechanism. Okay, follows free radical mechanism. Packing is not actually required, so you all can skip it also, but just know a reaction. Example, let us take, suppose you have CH3 CH2, CH3. What is this? Propane. Propane, let us take around 870 Kelvin. Decomposes to give you ethane. Then it can give you propene. So you can see ethane is lower, propene is same, but alkane only, simpler alkane. And it can give you methane, it can give you hydrogen. Clear? So this type of thing is called cracking or pyrolysis. Not at all used in our syllabus. So just know it and skip it. Okay. Next topic is aromatization. The last topic for alkanes is aromatization. What is aromatization? The word aroma I have told you. Aroma means some very nice smell. That is aroma, right? You say aroma is a nice smell and odor is a foul smell. So aroma is a nice smell and tization means making of that aroma. So aroma, so here we are not preparing scent or perfume, that aroma will come. We are preparing aromatic compounds. So the preparation of aromatic compounds from alkane is called aromatization of alkanes. Okay, this is nothing but preparation of alkanes from, preparation of aromatic compound, from alkane, from alkane. Now one thing you have to remember, that how many carbon containing ring it will be forming, 6 to 8. So that means 6 to 8 must be involved. So preparation of aromatic compound from an alkane containing 6 to 8 carbon. It cannot be like 12, 13. It's not possible. No, steric hindrance is also a factor. So preparation of aromatic compound from an alkane containing 6 to 8 carbons. Now you are going to prepare an aromatic compound and there is no catalyst required. That is not at all possible only, right? There has to be catalyst. So that catalyst is chromium oxide and aluminum oxide in presence of high temperature and catalyst. Okay, this is aromatization. Done. So preparation of aromatic compound from what? Alkane. Alkane will need to have some fixed number of carbons, because 13, 20, 25, which is very difficult. No, that will become polymerization, but not aromatization. So alkane containing 6 to 8 carbons. Done. In presence of high temperature, because you will learn in Haeckel rule of aromaticity. Later on I will talk about Haeckel rule. In Haeckel rule of aromaticity you will find that more the number of carbon it becomes, no, in stereo it will take different kind of shape, just like propylium ion I will talk about later on. Then you will find it will take a boat shape. So it's supposed to be aromatic, it's not aromatic due to high number of carbon. Clear? So 6 to 8 is maximum, not more than 8, because steric hindrance and shape will be distorted, no more planar, so it is no more aromatic. So in presence of high temperature and catalyst, this is aromatization. Now let's take an example, because without example real people don't understand anything. Example, suppose you have CH3, CH2, hexane, CH2, 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 CH3. What is this? Hexane. Now if I react hexane in presence of Cr2O3 and Al2O3 along with heat, then I will be getting benzene. What I will be getting? Benzene. Benzene along with 4H2. Clear? So what is happening is hexane is getting cyclized. The word is SCYCLISED, cyclized, to form benzene, and benzene is definitely an aromatic compound. Done. Now similarly, if I suppose I give you more than this, heptane, then what will happen? Benzene with a CH3 extra, that will become toluene. Clear? So you can understand, aromatization means alkene going to form an aromatic compound. If it is hexane, benzene, less than that not possible. From hexane it will start heptane, it will form toluene, and if you form more, it will be ethyl benzene, no more than that. Clear? Because in more than that it will not even planar only. Done? Understood? So this is the aromatization, where you have to prepare an aromatic compound from an alkane that will have 6 to 8 carbon in presence of high temperature. Temperature has to be high and there has to be catalyst. What is the catalyst? Al2O3 and Cr2O3. Clear? Any doubt? No doubt. This marks the end of our alkane. Our next topic is alkene. alkanes sorted out, we'll start with alkene now. Alkanes have been sorted out. Now we are going to begin with alkenes. Now let's see what we have in our alkenes. Before beginning with anything after this, I will be first discussing about the basic things about alkene which you have learned in class 10. So basic funda of alkene. What is an alkene? Double bond containing hydrocarbons are called alkene. You all know already what is an alkene because you have read it in class 10. So you have already read this in class 10. So if I talk about alkene, double bond present. What is the general formula for alkene? General formula for alkene is CnH2n. Right? So who is going to be the first member? Is it going to be methane? Methane cannot exist, right? So it's going to be ethene as the first member. So ethene is the first family member. Ethene is the first member. So this is the basic thing about alkene that you have already learned in class 10. Not going into much details of the class 10 things. Just to know that an alkene is a double bond where there will be double bond present. CnH2 is the basic general formula of this homologous series, and ethene is the first member. Methane does not exist. Clear? Now we'll be moving on to the preparation of alkene that we know very well. Our first topic is preparation of alkene. So let's move on to the topic preparation of alkenes. Where did it go? Just a minute. Extra ones. Okay, preparation of alkene. Preparation of alkene from alkyne. How will you prepare it from alkyne? How will you prepare an alkene from alkyne? By hydrogenation. By hydrogenation, right? So how? What is the basic funda? The basic funda is, suppose you have, first let me take up an example, a little better for you to understand. Example, suppose you have CH triple bonded CH, right? This is called acetylene. Hopefully you all know this, acetylene. So from acetylene, if I am using nickel in presence of some heat and obviously hydrogen also, then I will be getting CH2 double bonded CH2. This is hydrogenation. So this is, you are preparing it from an alkene. You are preparing it from an alkene. Now, could I make you understand? Did you understand that if you are going to prepare it from an alkyne, then you have to use this kind of nickel and nickel and hydrogen. It's called hydrogenation process. Acetylene in presence of nickel hydrogen will give you ethylene. No doubt, no problem is there. But the reaction will not stop at that point. The reaction will continue. So the reaction will continue to give ultimately alkane. But I do not want alkane. I want this ethylene only. So I have to stop the reaction ethylene. So to stop that reaction, I have to use some other catalyst, and that is where Lindlar catalyst comes into play. Clear? So whenever you are using nickel and H2, remember that the reaction will not stop at alkene. It will go to alkane. So this NiH2 catalyst you will be using when you are converting from alkene to alkane, not from alkyne to alkene, because reaction will not stop at alkene. Clear? So what catalyst I will use? I will use different catalyst. It's called Lindlar catalyst. So this we will not write for this. Okay? Clear? We will write Lindlar catalyst. Here, Lindlar catalyst. Lindlar catalyst. Then it will be stopping at this. Clear? If I use a Lindlar catalyst, then I will be getting an alkene only. Clear? So what will be the basic funda of this? Basic funda of this is, if I have to prepare an alkene from an alkyne, then I have to use Lindlar catalyst. Lindlar catalyst. Otherwise, reaction will not stop at alkene. It will continue till alkyne. It will continue till alkene. Clear? Now, what is the Lindlar catalyst? That only I did not say, right? What exactly is the Lindlar catalyst? So write down Lindlar catalyst. Lindlar catalyst is nothing but palladized charcoal. Palladized charcoal deactivated deactivated with quinoline. Quinoline. This mixture is called Lindlar catalyst. So please remember Lindlar catalyst because you have to use it in class 12 as well. So Lindlar catalyst is very important. Valorized charcoal deactivated with quinoline. Clear? Clear? Lindlar catalyst is paradise charcoal deactivated with quinoline. So this is very important. You have to remember this. Done. So this was the first method of preparation of alkene, that is from alkyne. We will be using Lindlar catalyst to stop the reaction at alkene. If you use nickel and hydrogen, I am repeating, if you use nickel and hydrogen, reaction will not stop at alkene, it will go till alkane. So we will not use that. Clear? Let us see what we have the next topic. Next topic is from alcohol, which is very easy one. From alcohol is very easy one. Let me give an example. Example, C2H5OH, C2H5OH in presence of concentrated H2SO4, in presence of concentrated H2SO4 gives you CH2 double bonded CH2 plus water. Any doubt? Then this is basically preparation of ethylene by dehydration of alcohol, right? Concentrated H2SO4 is responsible for dehydration. So we have done that dehydration simply. Clear? Very simple thing actually, not at all difficult. So if I have to convert alcohol ROH, then I have to use concentrated H2SO4 to convert it to an alkene. Whatever alkene, that depends on whatever is this R value, plus water. Okay, so ROH considers for alkene plus H2O. Clear? Okay, now here in case of alkyne, one thing I forgot to tell you, that I will tell you now. Alkyne Lindlar catalyst gives you alkene, and that alkene is actually a cis product. That alkene, if I go for stereochemistry, geometrical isomerism, then that will give you a cis alkene. Clear? So let me write over here cis alkene. Okay, let me take up a new page so that I can tell you more about this. Sorry, right? When I am using alkyne and I am using Lindlar catalyst, then I am going to get cis alkene. What I am going to get? Cis alkene. Now you know cis trans, GOC lecture, please go and watch. There I have told you cis alkene. So cis alkene, how it will look like? C double bonded with C, H, like this. It will be cis alkene. Okay, cis alkene. Now there is another case where we can get trans alkene. That is also from alkyne only. That we will get trans alkene. How? Let's check. This is called Birch reduction. What it is known as? Birch reduction. Birch reduction. This I have not told you there as a topic. I have not mentioned over here, but this will come under alkyne only. Okay. Birch reduction. Birch reduction is alkyne will react in presence of sodium slash liquid ammonia. Then you will get it an alkene, which will be known as trans alkene. Then you will get a trans alkene. Is it clear? So when you are reacting an alkyne in presence of any liquid, and you will get trans alkene, which is trans alkene. Clear? So suppose I have the reaction as RC triple bonded Cr, and I am reacting that with sodium and liquid NH3. Birch reduction conducted, so C double bonded C, R, H. Clear? This way it will be going to form, which is a very important thing. Please do not forget it. Birch reduction. Clear? So Lindlar catalyst giving you cis alkene, Birch reaction giving you transalkene. This question might be asked. Okay, name reaction can be given Birch reaction. So in that case, please remember that transalkene and cisalkene. Done. Alcohol understood. That from alcohol dehydration reaction if you conduct, then you will directly get an alkene. Next is alkyl halide. Example first. Let us understand with an example. C2H5Br, C2H5Br, ethyl bromide, and I have to take it to ethene. Last time, if you remember, in alkane, I have given the same reaction and I have told you to go to ethane. Then you have used Grignard reagent, right or wrong? This same question, if you go to ethane, you will get Grignard reagent you have to use. Then only you can go to ethane. But this same thing, same halide, I will go to ethylene. Where I will go to ethene or ethylene, whatever you say, I will go to ethylene. So what do you have to use? I will not use Grignard reagent because that will give me alkane, but I don't need alkane, I need alkene. So for that, I will be using alcoholic KOH. Alcoholic KOH. So if I use alcoholic KOH, what will happen? It will form CH2 double bonded CH2 and HBr will go out. Please remember, HBr will go out, but this HBr ultimately, this HBr reacts with the KOH part. It will react with the KOH part and ultimately form KBr plus water. Okay. Because acid plus base reaction forms water plus salt. This will form KBr plus water. Okay. Now tell me, any doubt? Any doubt? No doubt. Everything is balanced. Also check properly. Everything is balanced. So C2H5Br in presence of alcoholic KOH gives you CH2 plus KBr plus H2. Now, if you miss out the word alcoholic, you will get 0. Why? Because there are two types of KOH we will be seeing. One is alcoholic KOH, one is aqueous KOH. If you miss out the word alcoholic, you will get a big 0. So please do not miss out that. Okay. So if it is something like RX and you use alcoholic, and you use alcoholic KOH in that, then you will get an alkene along with KX plus water. Okay, clear? Alkyl halide clear? So sir, alkyl halide to alkane, Grignard reagent, alkyl halide to alkene, alcoholic KOH. Understood? Any doubt? No doubt? Very good. Let's move on. Next we have coal-based electrolytic method. If you have remembered, then we have used coal-based electrolytic method to prepare alkene. Then what we have done? We have used 2-RCONA, and we have done electrolysis to get the required alkane. Right? In case of alkene, we will be also using obviously sodium salt, but we will be taking a little different one. How? We will be taking some salts like, we will be taking up, let us take CH2, that is an example only. Here I will be showing you with an example only, not a basic funda I am giving. Okay. CH2, suppose the reaction is CH2 COOK. I am taking a potassium salt. Last time I have taken one sodium salt. Okay, here you can see that I have taken two salts only, but they are bonded to each other. Can you find? Last time I have taken 2 times RCONA. Here I have taken already 2 molecules only. See, but 1 molecule, but they are having 2 things. So this is 1 only. So I have taken them, right? So this one, if I do electrolysis, directly if I do electrolysis of this, then what am I supposed to get? I am supposed to get CH2 double bonded CH2. If we write it beside only better. CH2 double bonded CH2 plus what will be formed? KOH plus 2CO2 plus hydrogen. Whatever it was previously, it will be the same. Right? Understood? Now what else is there? Electrolysis in presence of water. So water is also there. That's a factor. Done. So this is a basically coal-based electrolytic method. Now what exactly is happening at the cathode and anode? Hopefully you all know that same thing as previous. Cathode, what will happen? Hydrogen gas will be released. So cathode H plus 2 electrons forms H2. Done. And at anode what happens? At anode the CH2 COO minus CH2 COO minus plus 2 electrons forms CH2 double bond CH2 plus 2 CO2. Done. And the leftover OH minus ions and K plus ions forms KOH. Okay. Now balancing also you have to do, right? So here we will put a 2. 2 CO2 already there. Hydrogen 4 plus 2. How many? 6. 6 hydrogen. 2 plus 2 4. 6 8. How many over here? 4 plus 2 4. 2 plus 2 4. So I will put over 2. 2, 1 2 3 4 5 6. 2 2 6. Done. Clear? Balancing done. Balancing also to do now. This is the thing happening in cold way, right? Last time, you remember we took RCONA. This time we did not take RCONA. We have taken CH2COK. We have taken another CH2COK. They are already bonded by a single bond. Last time there were no bonded type. Clear? Understood with this? This is Kolbe-Aromatic preparation for preparation of alkene. Done. Let's see what we have next. Next we have chemical properties of alkenes. We are done with the preparation of alkene. Now we will be moving on to the chemical properties of alkene. First step is hydrogenation. Hydrogenation is basically nothing but addition of hydrogen. Addition of hydrogen. Addition of hydrogen. Now you tell me, addition of hydrogen, general formula for alkane is CnH2n. Now if you are adding hydrogen, then definitely it will be changing into CnH2n plus 2, because you cannot add more than that, because this is alkane, the simplest one. More than that is not possible. So definitely it will change to an alkane only, right? So how many hydrogen it can add? Maximum of 2 hydrogen it can add. So what will be the funda is, if you are taking a alkane, if you are taking an alkene, and if you are treating it in presence of nickel and hydrogen at heat, then you will be getting an alkene, right? This is the basic funda. This is the easy funda. No problem with this. That is an easy one. Alkene in presence of nickel and H2, I am going to get alkene. Last time, if you remember, Lidler catalyst we did, because that was an alkyne and we had to stop the reaction of alkene, sorry. And this time we are not doing so. Clear? Done. So very simple examples will be asked from here. Very simple, very simple. Like suppose I have CH2 double bonded CH2 and I am converting it to alkane. So it's a CH3 double bond CH3. Then double bond will break and ultimately it will form one. It will add 2 hydrogen in that place. Then hydrogenation reaction is clear. Okay. Right. Now here I am making a box and writing characteristic property of addition reaction. Addition reaction. Last time, if you remember, I have told you about substitution reaction. Characteristic to only alkene. Characteristic to only alkene. Addition reaction is characteristic. Addition reaction is characteristic to alkene and alkyne. They will undergo addition reaction. Why? Now you see, you have eaten too much. Pet bhorti hoye gache already. So can you eat more? No. Your pet is already bhorti, so you cannot take in more hydrogen, right? You cannot make your general formula CnH2n plus 4. Does not exist, right? But this UPUC, they are having double bond. So that means their pet is khali. So they can eat more. So they can break the double bond and they can add 2 more hydrogen to form single bond. And similarly, alkene is having 3 bonds. This triple bond. So it can break 2 bonds ultimately to form one alkene. So they can add 4 hydrogen. Clear? So addition reaction is a characteristic to alkene and alkyne, while substitution reaction is a characteristic to alkanes. Clear? Understood? Next, let's move. Addition of halogens. This addition of halogen is a distinguishing test between unsaturated compounds and saturated compounds. So please note down, differentiating test. Differentiating test between saturated and unsaturated compound. Clear? So how will you differentiate between a compound which is saturated and unsaturated? Obviously not by writing its chemical formula, because in the lab we will not get to see it. So you need to understand by some test, there is a chemical test. So differentiating test between saturated and unsaturated compound is addition of halogen. Why? Why? Very simple question and a very simple answer to it also. Alkane is not undergo any addition reaction. That's just now I said, no, its pet is bhorti, so it cannot take in anymore. So even if you give it halogen, it cannot take in. It can substitute it, right? Because they undergo substitution reactions, they can substitute it, but they cannot add it. So we will not get any visible change. What do I mean by a visible change? Achha, suppose we are taking bromine, the color of bromine is then reddish brown. So if we are taking reddish brown and we are taking, let us take methane and we are adding it to it, we will not find any change in that reddish brown color, because it will not undergo any addition reaction with that. But if we use ethylene and treat it with bromine, we will see the reddish brown color of bromine fades away. Why? Because it is performing addition reaction. So that's the difference between unsaturated and saturated compound. Clear? So addition of halogen is serving as a differentiating test between saturated and unsaturated compound, which I have done in class 10, but still I am telling because question might come from here. Okay, so it's very simple over here. If you are taking an alkene, so let me write over already. If you are taking an alkene and you are treating it with Br2 in presence of CCl4. Actually, addition of halogen can be done in two ways: by using a non-polar solvent, by using a polar solvent. Clear? This is using a non-polar solvent. Polar solvent will be coming a little bit later when I will be talking about HOCl. Here you see addition of HOB or HOCl. This is polar solvent, and this is non-polar solvent. Okay, so if it is adding in non-polar solvent, then what will happen? This I have to show you by example. General formula I cannot give you for this. Okay. Suppose the thing is CH2 double bonded with CH2. Okay, and I am treating it with Br2 in presence of CCl4. Please note that this is a non-polar solvent. A non-polar solvent. Okay, so what will be formed is CH2 Br and CH2 Br. Clear? CH2 Br this side and 1 Br that side. So this is nothing but 1,2 dibromo methane. Understood? So if it is asked ethylene to 1,2 dibromethane, simply we will be using Br2CCl4. Any doubt? I hope no doubt. Similarly, we can do for iodine. Then iodine and chlorine as well. Okay, here iodine you can use iodine, chlorine, but chlorine will not use because it is explosive. Clear? Addition of halogen done. Clear with it? Done. Okay, next. Hydration reaction. Addition of H2O is also known as hydration reaction. Right? Hydration is always related to water. So please remember that whenever I am talking about hydration, that is related something related to water. The addition of water is known as hydration reaction. Now, you tell me, how does water dissociate? Everyone knows, right? In ionic equilibrium, so every time we will be using this on the water dissociation. H plus plus OH minus, right? So you tell me, if I have an alkane, an alkene, suppose CH2, if I treat it with water, what will happen? What will happen? One side H2 must go, H plus will go, and one side OH minus will go. That's the point. That's the point, right? But water will not usually dissociate into this. Even if it dissociates into this, it's fine. It will dissociate, but the H plus furnished will be quite less actually. Okay, so what we will do, we will use a H2SO4 as well. Fine, we will use H2SO4. I am not saying that H plus is less, very less, not there only. No, it is there, very much it is there. But we will be using an H2SO4 as well with this. Okay, so CH2 double bond CH2 H2 in presence of H2SO4. Why? Because you will find mostly we use H2SO4 as a proton donor, because this is acid, so easily it will dissolve in that to give more H plus, more and more H plus. So there will be plenty of H plus. That is what I am saying. Okay, so H2SO4 you use in presence of water, then it will dissociate as H plus and OH minus, H plus and HSO4 minus. So it will be better for us, no? More and more H plus. Plus 2 H plus will per mole, diabacic acid. So this will form CH2. What will happen? Bond to broken already. So what will happen? One side H will go and add, and another side there will be the OH going to add. This will be the compound. So let me write it in a formal way. This will become CH3, and here the OH will attach will become this. Clear? Doubt? No doubt? None? Clear? Ethylene? Understood? Very good. Acha, now you tell me one thing. Whatever compound I have been discussing till now, here you see CH2, CH2, here you see CH2, CH2, here you see CH2, CH2, all are symmetrical compounds. What about asymmetrical compound? Now, what do I mean by asymmetrical compound? That is also a very big question, right? Okay. Let me take up two separate examples now to make you understand. This is also an important part actually. Okay. Here only I am taking a second example. Suppose instead of CH2 CH2 I have CH3 CH double bond CH2, and this I am reacting with Br2 in presence of CCl4. What will happen? Achha, sir, bond will break. CH3 CH3 CH CH2, bond to broken. Yes, correct. Br will attach over here. Br will attach over here. Right, done. Solved. Now naming, I basically have learned. So please name it. 1, 2 dibromo propane. Doubt? No doubt. Done. Fine. Very good. Correct. Now let us come here. Here also let us take the same example. CH3 CH double bond CH2 in presence of water as well as H2SO4. Right? What will be formed? CH2 CH3 CH single bond CH2. Right? Now this side I will attach the H or OH, or this side I will attach the OH. That I have to think. This side I will attach H, this side I will attach OH, or the ulta. This side I will attach OH, this side I will attach. Which side? Someone can say this side I will attach, someone will say this side I will attach, someone will say this side, someone will say this side. Which side? Both sides to it will be. Both sides it cannot be, na? Both sides only H I have added. That cannot be possible. One side I have to keep OH, one side I have to keep H plus. Then which side I will keep that? That is dependent on which rule? Markovnikov's rule. What is Markovnikov's rule? Don't fall from the sky, because in GOC lecture only I have told you what is Markovnikov's rule. Markovnikov's rule is going to say that when you are adding something, the negative part of the addendum will be attaching to that carbon which is containing less amount of hydrogen, right? That is Markovnikov's rule, written in GOC lecture notes. Please go and refer to the notes already written there. Still I am mentioning over here Markovnikov's rule. In short I am writing Markovnikov's rule. Markovnikov rule. Negative part attach to less hydrogen wala carbon. Right? Negative part attached to the less hydrogen wala carbon. Recalling Markovnikov rule, and anti-Markovnikov is just ulta, where there is more hydrogen attached to that, and that is taking place in case of B, HBr and H2O2. Right? Clear or not clear? Markovnikov rule, negative part attached to the less carbon wala hydrogen, less hydrogen wala carbon, right? That I have told you in the GOC lecture. So if you have not understood, please go and watch the lecture. Okay, so which side should I attach the OH? The OH I will attach on here. OH I will attach where? OH I will attach here. So what will be the final answer to the question? The final answer to the question will be CH3 CHOH, now a single bond CH3. Clear or not clear? So this is going to be the major product. It's not like the OH will not attach to that carbon. It will attach, but that will be a minor product. Major product is going to be this CH3 CHOH CH3. Clear? That will also be formed. But when we will write in our examination, we will write for the major product only, not for the minor product. Clear? So hydration reaction understood? If it's a symmetrical one, it's a very simple one, ethylene, no problem. Any side you attach. But when it is an asymmetrical one, then you have to follow Markovnikov rule, which is going to say that negative part will attach to the less hydrogen wala carbon. Clear or not? Clear? Next. What we have next is addition of HOBr HCl. Okay. This is also the same thing I will say. Differentiating test between saturated and unsaturated compound. Clear? But that is not mentioned because generally for that we use Br2 CCl4, non-polar solvent. Okay. Okay. So this is addition of halogen. I am writing addition of halogen in polar solvent. Addition of hydrogen in polar solvent. Just this. This is addition of halogen only in polar solvent. Fine. So if I have suppose CH2, presence of CH2, and I am giving HOBr, what will be formed? One side it will be CH2 single bond CH3, and one side it will be an OH attaching. Clear? CH2 CH2, one side it will be a Br attaching and one side it will be a OH attaching. Clear? One side will be a Br, one side will be a OH. It was supposed to be 2 Br, no, but 2 Br won't be attaching. One side will be Br, one will be OH minus, because nucleophilicity of OH minus is more than Br minus. That is why one Br minus will not join. Okay. Achha, remember in GOC I have told you that when a double bond breaks, A double bond B, then arrowhead, whoever is facing the arrowhead gets a negative charge and another person gets positive. This type of thing happens. I have told you that this type of things happen. So similarly the bond breaking, so one carbon is getting plus, one is getting minus, so there must be a plus one, that is electrophile, and there must be a nucleophile attacking, then only it will be possible. So this Br must be a electrophile, this OH minus is a nucleophile. So Br minus nucleophile will not be able to attach because nucleophilicity of OH minus is more than Br minus. Clear? And the Br plus is coming and attaching. Br bond, this Br bond, one has this delta positive, delta negative. This delta positive one is this, which is going to attach. This delta negative one cannot attach. This delta negative one cannot attach. Why it cannot attach? As nucleophilicity of nucleophilicity of OH minus is greater than Br minus. Clear? Nucleophilicity is the rate of giving electrons. Nucleophile does what? Gives electrons. Na? So nucleophilicity is giving electrons. OH minus can give more electrons than Br minus. Readily it can give electrons. That is why instead of Br minus, OH minus is coming and entering. Clear? So one Br and one OH. This is the basic thing of polar solvent. In presence of polar solvent, this is the only change that happens in case of polar solvent. Otherwise, if you find there is no such change. Whenever you are using halogen acids, same thing. This is actually halogen acid only. Achha, clear with this or not? Clear? So when you are using HOBr or HOCl, then one OH, one Br. If you are using normal one, Br2 CCl4, it will be both Br. Okay. Achha, this can be written in another format as well. What is another format? If I write Br2 in presence of H2O, then that is also the same thing. H2 is a polar solvent and I am adding bromine in presence of polar solvent. So that will also give me the same result. Please do not get confused. It will give me the same result. Same result means CH2OH, CH2Br. Clear? Same result. Just the representation of the reagent is different. Nothing else. Clear? Clear or not clear? Tell me. Addition of HOBr, HOCl. Clear? Very good. Very good. Next, coming to oxidation. Oxidation. Very important for one reason, because this also serves as a differentiating test. Okay, but we will be studying oxidation under two headings. We will be studying the oxidation using KMnO4. Okay, using the KMnO4 only. You can also use K2Cr2O7, that also does oxidize. We will be talking right now about KMnO4. You can use K2Cr27 in your answer. Okay, KMnO4 slash K2Cr2O7. Both are oxidizing agent. You will be studying in the D block. In class 12, you have a chapter D and F block, but you will be studying about MnO4 and Cr2. Bromotate and manganate there. Permanganate and dichromate there. We will be discussing about this. Okay. So first case, what I am going to take out is, see the words are very important. Cold, alkaline, dilute KMnO4. Cold alkaline, dilute KMnO4. Cold alkaline, dilute KMnO4. If I am taking cold alkaline, dilute KMnO4, what will happen? If I am taking hot concentrated KMnO4, what will happen? You will get to see a major difference between them. This cold alkaline cold alkaline dilute KMnO4 is called Bayer's reagent. What it is called as? Bayer's reagent. And the test that follows is Bayer's test. And the test that follows is Bayer's test. Bayer's test. What does Bayer test follow? Class 10. Done already in class 10. Differentiating test between again what? Alkane and alkene, or alkane and alkyne. So differentiating test between saturated and unsaturated compound. Right or wrong? Saturated and unsaturated compound. So we have two methods for differentiating. Between saturated and unsaturated compound. Either use Br2CCl4 or use Bayer test. Now what exactly is Bayer test? We need to know now. So what is the Bayer's reagent? Cold alkaline dilute KMnO4. If you miss out one word, it will be wrong. Because if you miss out cold, dilute KMnO4 is what? What is that? Wrong. It will be hot alkaline dilute KMnO4. Right? Okay. Let's write Bayer's test. Suppose we have CH2 double bonded with CH2 and we react it with cold alkaline dilute KMnO4. Cold alkaline dilute KMnO4. Then I will get CH2OH, CH2OH. Clear? 2 times OH will be attached. Whenever bond will break, both sides OH will attach. Please remember that whenever cold alkaline dilute KMnO4 are using, bond breaks, both sides OH attaches. But done. Clear? Along with this, two other products will also form. That is 2MnO4, 2MnO2 plus 2KOH. Understood? Not understood? Simple thing. Now let me tell you a few important thing, that is I am writing here. See here, if suppose I have one carbon bonded with a carbon, here I have let's take OH and I have OH. Okay, this is called if the OH groups are present on just adjacent carbon. It means two side by side carbon or two consecutive carbon, then we will say it as vicinal position. Vicinal, and since it is two hydroxy group, so all diol. Clear? So what did you understand? That if two OH group present on consecutive carbons, that is vicinal diol. Clear? So what is vicinal diol? OH present on two consecutive ones, vicinal diol. Now similarly, if there is COH, OH on the same carbon, if there are two, if there are two OH groups, on the same carbon if there are two OH groups, then we call it as geminal. Diol. What do we call it as? Geminal diol. Put spelling, I don't really remember the spelling, but it is G or Z, but I'm writing Z for now. If spelling is wrong, let's correct it. Okay. Geminal diol is not possible. Please remember this, that geminal diol is not possible. This structure is not possible. Geminal diol is not possible. But geminal position, you have to remember. What is geminal position? Same carbon, two same things are present. The geminal position, adjacent carbon, same things are present. Vicinal position. Geminal diol is not possible. Water will move out and ketone will form. Okay. So this is, what is this? This is vicinal diol. So vicinal diol can be formed from here. Clear? So if it is, we are forming from an alkene to vicinal diol, we will be using cold alkaline dilute KMnO4. Remember this, very important one. So clear? So cold alkaline dilute KMnO4 Bayer test to distinguish between unsaturated compound. This is the reaction happening. Then next we have the case number 2. Case number 1 we discussed cold alkaline dilute KMnO4. Second case we will be discussing is hot concentrated KMnO4. First we discussed about cold dilute alkaline KMnO4. Now hot concentrated KMnO4. If we use hot concentrated KMnO4, no, direct oxidation will happen. Highly oxidizing agent. Please remember this, very important. Okay, highly oxidizing agent. strongly oxidizes. Strongly oxidizes. What does it oxidize? Here too we did not find any oxidation happening. Here also we did not find such oxidation happening. Just two H are entering. What do you mean by strongly oxidize? Let me give you the example. Then you can understand how strongly it can oxidize. Suppose here I am writing the example. Okay, C2H5OH. If I treat it with hot concentrated KMnO4, what will be the product? Product will be CH3COH. Now tell me how? It is such a oxidizing agent. Directly the product will be CH3COH. Clear? And water though will be there, that you balance it. Well, balance is already balanced. Clear? So you can understand how it is being formed. So C2H5OH directly forming carboxylic acid, where we have to oxidize using two steps. First then go to aldehyde, then go to carboxylic acid. Aldehyde directly went to carboxylic acid. It's a very strong oxidizing agent. So that is why it directly went to carboxylic acid. Right? Clear? This was an alcohol. But we are dealing with alkene. So let me show you with an alkene as well. CH2 double bonded with CH2. If I use this and if I use hot concentrated KMnO4, hot concentrated KMnO4, you can see CH2 double bond CH2 groups are there, and this also double bond CH2 groups. Then these two are oxidized to carbon dioxide plus water. Clear? Hydrogen how many? 4. Here how many? 2. 2 to 4. Done. Understood? Whenever double bond CH2 groups are present, all oxidized to carbon dioxide. This I am writing over here. Remember this very important thing. Let me first get a box. Where did the box go? Double bond CH2 oxidized to CO2, and whenever CO2 is formed, water to will form. So CO2 plus water. If it is double bond C H and there is an R, and there is an R, then it is oxidized to RCOOH. Clear or not clear? If it is RCH, it is going to be oxidized to this case, RCOH. Done. And if it is both sided R, that means this side also R, then it is oxidized to ketone. Clear or not clear? Then it will be oxidized to what? It will oxidized to ketone with the R containing both sides. Understood or not understood? So if it is double bond CH2, one to directly CO2H2. So last you can see it has gone to CO2H2. If it is CHR double bond, then it is RCOH, and if it is R, both side R, carbon double bonded, then it will go to ketone. This is the most important thing. Very strongly oxidizing agent that will directly converting to carboxylic acid. Clear or not clear? Understood? So you have to use two cases. One is called alkaline dilute KMnO4 pairs reagent. Second one is hot concentrated KMnO4 directly to convert from alcohol to carboxylic acid. Clear or not clear? Geminal vicinal position understood. Geminal diol is not possible. Vicinal diol is possible when you use cold alkaline dilute KMnO4. Clear? Any doubt is there? No doubt. Okay, let me show what's ozonolysis. Ozonolysis I am starting. Before that, let me show one more example. Though I don't think I need to show any more example, but still I am showing. Let me quickly erase this. Example. Suppose I have CH3, CCH3 double bonded with CH2, and I am treating it with hot concentrated KMnO4. What will it form? You can see both sides are, so it will be of ketone. So it should form ketone will form or something else. Tell me what it is supposed to form. What it is supposed to form, ketone or something else? It will not form ketone. It will not form ketone. You might say that RR is both side and carbon is double bonded. Fine. But double bond CH2 is also there. Check na. Double bond CH2. Who will see that? I will see. So double bond CH3 will form COOH. CH3 COH. Done. Water will form and CO2 will form. Done. Clear? Then clear or clear? Understood? Okay, fine. Okay. Okay. Clear? Done. Another reaction you can take, suppose you are taking CH3, CH2, same reaction, CH3, CH3. If I use KMnO4 and heat, then I will be getting CH3COH plus H2O plus CO2. So just both the reactions are the same. What did you do? I did one mistake. That is from my side. So I apologize for the mistake. This will be giving you this product. This will not be giving you this product. Okay? And you were right. I was wrong. I apologize. What will be the answer? The answer is very simple. Ketone. C double bond O, CH3, CH3. I apologize for the mistake. This will be the ketone and second one will be the carboxylic acid. Clear or clear? When you are using only KMnO for heating, then you will get carboxylic acid because it is not hot concentrated mentioned. But when you are using hot concentrated, ketone will form because ketone is there. But you can see C double bonded part is there. Right? Understood? Clear? Next is ozonolysis. What is ozonolysis now? Acha, name is ozone. Ozone is what? O3 and lysis means bond fission. So ozonolysis is breaking of bond using ozone. Breaking of double bond using ozone is called ozonolysis. Very simple. We have two types of ozonolysis in our syllabus. JEE syllabus, not here. In JEE NEET syllabus, we have two types: reductive ozonolysis and oxidative ozonolysis. Now, oxidative ozonolysis is not difficult. Actually, why it will be difficult? It is only ozonolysis only. Just in the last step, you have to oxidize it, and oxidizing that you have done over here using this two. You have to done understood only who will be oxidized to what. Alcohol is oxidized to aldehyde. Aldehyde is oxidized to what? This you all know in oxidation. So that oxidation you have to do in that last step. We will be doing oxidation, but luckily we do not have that in syllabus, so I will not discuss about that right now. Clear? I will be reading about reductive ozonolysis, oxidative ozonolysis to not be taken into consideration now because we don't have it in our syllabus, in our school syllabus, not in JEE syllabus. Okay. So ozonolysis. What do you mean by ozonolysis? But let me just give you a rough summary. Ozonolysis means breaking unsaturation by ozone. Okay, so you're using ozone to break unsaturation. It is ozonolysis. Very simple. Explain with an example only. Suppose you have ethane. First I will explain with you a basic one, then I will be taking you to a more advanced one. Suppose you have CH2. Then suppose you have CH2. Okay. When you take it as ozonolysis, in your exam paper you will be finding it as given as 1 O3 2 Zn water. This thing. Fine. This thing you will get. In your paper, you will get in this format. So you have to write the final answer. But now I will not tell you directly the final answer. I will be telling you how will you get to the final answer. In exam, you will directly get the final answer. You will directly write it as HCHO plus CH3CHO. Directly we will be writing it as this. And H2O2 don't forget. Okay. If you forget H2O2, gone. There only you will be gone. So what do you need to read first of all? First of all, two things to remember in ozonolysis. Number one, H2O2 is produced as byproduct, which you cannot forget to write in the exam. Produced as a byproduct, which you all forget. Second, ozonolysis produces only aldehyde or aldehyde and ketone. aldehyde and ketone. So ozonolysis will give you only aldehyde and ketone, nothing else. So just relax. I am talking about which type of ozonolysis? Reductive ozonolysis, not oxidative. Because oxidation you can do. See, aldehyde oxidation you will do, you will get CO2. HCH oxidation is CO2, and CH3CHO is you will get next step is CH3COH. That thing you have to understand. Okay. Which type of ozonolysis? Reductive ozonolysis, not oxidative ozonolysis. I'm mentioning it also here because many are GS students, no? Okay, clear? Okay, let's take CH2 double bond CH2. First step is O3. So when you are reacting it with O3, no, what happens is if there is a double bond completely breaks off. No bond exists between CH2 and CH2 anymore. Both the entire bond is gone. If it is a triple bond, one single bond will remain. In case of double bond, nothing remains, gone. So what will be formed? CH2. Remember, a house is formed. How does a house look like? Like this. This is a simple front view of house. হাউসের সামনের দিক দিয়ে এরকমই দেখায়, পিছন দিকে আরো কিছু আছে এরকম। আমি ছবি আঁকানোর দিন ছেড়ে দিয়েছি এরকম। দিস ইজ আ হাউস, নো? পিছনের পার্ট ছাড়ো, সামনের পার্টটা দেখতে এরকম হয়। সো আই হ্যাভ টু মেক আ হাউস। I have to make a house. So how will you make a house? We using oxygen will make a house. So here, house made. That's a house. That's your house. Next step, you will be using zinc, water. Remember, when you are using zinc and water, this part breaks off and this part breaks off separately. Clear? This part breaks off and this part breaks off separately. So this part will give you HCHO. This part is HCHO and this part is also HCHO, and byproduct is H2O2. Clear? Then this is all about ozonolysis. So did you all find the mistake I have made? Did you all find the mistake? I have written CH3CHO. Though it is not going to be formed as a product of CH2CH2. Clear? So quickly let us change that to HCHO. HCHO plus HCHO plus H2O2. Done. Yes, understood what is exactly happening. So you are building a body, you are breaking the body to get the final product. This is reductive ozonolysis, simple as that. Okay. Okay, we have alkyne next. Before that, let me do another case of ozonolysis. Another example, let me take. I do have a page is here. Another example of ozonolysis. Suppose I have CH3, CH, CH2, O3. What will you form? Body. So I have to build a body from this side. Remember, no bond will exist, huh? In case of alkyne only the bond will exist. Here no bond. Done. Body you have built. Very good body you have built. Next step what will I do? Zinc water I will treat it with. So body breaks from this side, body breaks from this side. So this side what I am getting? CH3CHO, very clearly visible. CH3CHO, and this side it is visible HCHO. Done. And final product also H2O2. Done. This is the answer. Very simple analysis. Now where is the problem arising? Tell me. Where is the problem arising? You know, if you are given this compound CH3 CH double bond CH2, you can tell me the answer is CH3 CHO plus H2 plus H2O2. Now how about if I give you the answer as CH3 CHO plus HCHO, the products of one compound, find the compound, then how will you go back process? How will you go? Did not understand the question. The question is, if I give you CH3 CHO and HCHO and I ask you what was the original compound, then how will you go back? How will you go back? It's very simple, don't worry. You see, oxygen কোথা থেকে উদয় হয়েছে? Oxygen has been coming from this position where the double bond was initially there. So let's put the two oxygen together and make a double bond. Like if the question is CH3 CHO is given, CH3 and HCHO is given, find the original compound. Back process if I have to go, then what will I do? Let me write here back process. Back process. Then I am given with a compound CH3CHO and HCHO, so I will be writing it as OHC like this. This two oxygen I will be taking together And what I will be doing is I will be writing it as CH3 CH double bond CH2. But see, the original structure is come back. This is as simple as this. Even if it is a back product, no. Even if it's a product given, do the back procedure and get to the compound. Because some questions are like this, will be asking the question. That you have to clear. So what you'll be doing? Simply oxygen is there. Just make that oxygen together and send it back. Nothing is there. Clear or not clear? Clear? Now, ozonolysis only. One khatarnak question let me show you. Before starting with alkyne, let us do some question of ozonolysis. Wait. Reactive influence. See here. This type of question. This type of question can come. Purely ozonolysis based question. But you have to use a little bit of your brain. Unsaturated hydrocarbon adds two molecules of H2 and non-reductive ozonolysis gives butane 1,4 dial ethanol propanol. So you can see three things they are giving. Okay, give the IUPAC name and structure of. Now tell me what will happen. See, three things they are giving: butane 1,4 dial, ethanol, and propanol. So these three things they are giving means must be there are two double bonds in the entire compound. There are two double bonds, right or not? Secondly, IUPAC name I have to say. Thirdly, structure, and lastly I have to show the reaction also. That means the reaction also I have to show. Clear? Acha. Reaction part, I hope if you are getting the original compound, reaction part won't be a problem for you. First, let's try to get the product. What is butane 1,4 dial? First, someone tell me what is butane 1,4 dial. Butane is C as far as I know. Acha. Here you can do rough work, because they are not asking for the procedure. They will be taking your final answer because marks are given the final answer only. So in rough, ignore the hydrogen. That will create a chaos. But in the final case, IUPAC name and structure when writing, you have to show the hydrogen because there you will not get the marks. Clear? So this is butane. Now what is asked? 1,4 dial. Al is aldehyde. So first position al means C double bond O H. Done. And second is fourth. So 1, 2, 3, 4. This side also it is there. Done. This is the first case I have got. Next is ethanol. Ethanol to you all know. CH3CHO. Done. And another one is propanol. Propanol is CH3COCH3. Done. So what I need to write it? I need to combine it in such a way that all the oxygen is done. Gone and dusted. So how will I combine it? Tell me. I can write it like this. See here. CH3CH. O, and this O I am writing like this CCCHO. Okay, one compound or not. And here this oxygen I am writing it. Okay, oxygen, double bonded oxygen with a carbon CH3 and CH3. You can see the compound উল্টো করে দিয়েছি, কিছু করিনি, কম্পাউন্ডটাকে উল্টো করে দিয়েছি। Why did I put a double bond here suddenly? কম্পাউন্ডটাকে জাস্ট উল্টো করে দিয়েছি এখানে, ঠিক আছে? হলো? তাহলে this will be one thing, this will be one thing. So what will be the actual compound? CH3 CH double bond CH CH2 CH2 CH double bond C CH3 CH3. This will be the check. Hydrogen, if I made any mistake, forgive me, forgive me for making any mistake in hydrogen. IUPAC name of the structure to you will write that I will not take. And this is the structure. What is IUPAC name? That I have to also write. What is IUPAC name? 1, 2, 3, 4, 5, 6, 7, 8. 8, 2 methyl, 1, 2, 3, 4, 5, 6, 6. So it is 2 methyl, 2,6 di N 2,6 di N octet লিখতে 2,6 2 methyl octane 2,6 di N. Now take So it is octane won't be there. Ignore that in, huh? Enta hobe na ekhane. Octa 2,6 right. Done. So you can understand back process how it works. Now it is your duty to form the reaction. Reaction I will not do. Reaction you will do. Do the reaction. Writing here. Reaction homework. Reaction you will write at homework. The main thing I have solved. So clear with this how to solve. Just whenever you find the double bond oxygen, just merge it up and form a double bond. Okay. Acha. Clear. Understood. Okay. एक और क्वेश्चन करें. Let's do one more question. What do you say? হয়ে যাবে একটা কোশ্চেন করা যাক তাহলে দেখি. Let's try out another question. This is the question otherwise you structure. হ্যাঁ ঠিক আছে. Let's do this question. কোথায় গেল? হারিয়ে গেল. তাই বসে পড়লো. কোথায় গেল? কোশ্চেনও হারিয়ে যায় আজকাল. Let's try out the question. Propanol, propanol and pentanthreone are the authorized product. Same question, same type of question now. Propanol is propanol is what? CH3, CH2, CHO. Propanol and pentanthreone, then C double bond C double bond O C C. This way. Right. So CH3CHO and this O I have to write O double bond. Baba, how many O? C. Now you see, ছবিটাকে যদি আমি ঘোরাই তাহলে what will happen is I will get 2C like this and I will get 2C like this. হবে কি হবে না তো? হবে তো? ছবিটাকে ঘোরালে পরে দুটো তলায় দুটো এভাবে থাকবে তাহলে এটা হবে. তাহলে this thing will be double bond. So the structure will be CH3 CH2 CH double bond C CH3 CH3 যেখানে একটা H হবে CCH3 CH3 and there will be CH2 CH3. Clear? So this is going to be the structure. Tell me, clear or clear? Clear? So this is going to be the ultimate structure. Now IUPAC name depends on you. Please write IUPAC name. If you have any doubt then tell me. But IUPAC name your time. Now let me give you homework for IUPAC. IUPAC name. Comment. Comment on the IUPAC name. What is going to be the IUPAC name? Comment. Your homework is to comment the IUPAC name of this structure. Clear? This type of questions will be asked. Very easy type of question. Okay. Let's see if I have any other question, and we'll begin with alkyne. These are conversion type question. This I will do at the end of the lecture. Okay, at the end of the lecture, I will be discussing this type of conversion type of question, that we can recall everything what we have done. Friends, write structure and name of product obtained by reaction of Na with mixture. This is the Woods reaction question. Fine, let's do this. This question is actually from Alkane. We did not do it. The Woods reaction question, no, from Alkane it has been asked. From Alkane, Woods reaction. To reaction was the first reaction. Decarboxylation. No. Woods. This is the Woods reaction I've discussed. Now let's solve this question. This question was supposed to be solved here, but we did not do it. Never mind, no problem. See here. Structure and name of the products obtained with reaction of Na with a mixture of 1 iodo, 2 methyl propane and 2 iodopropane. This type of question is very important question. Okay, because this was homogeneous. Now if it is not homogeneous, then what will be formed? Then 3 products can be formed. 3 different types of product. Before solving the question, let me tell you about that also. There is a slide provided. Empty slide. Clear? Suppose it is not a symmetrical one. What do I mean, sir? Not a symmetrical one. Suppose I am using Rx plus R dash X and I am treating it with Na in presence of dry ether. So what it will form? It will form Rr plus R dash plus R dash. There are three different products it will form. Then it will form 2NX. So this also you need to remember that when R and R dash they are not equal, then what will happen? This condition is for when R dash are not equal to R dash. That means R and R dash they are two different alkyl groups. So in that case three products will be formed. This is the funda over here. Okay, example দিয়ে একটা দেখিয়ে দিচ্ছি, ঝট করে দেখে নাও. Suppose it is CH3 Br plus C2H5 Br. Okay, forming in presence of Na dry ether. So কি form হবে? Form হতে পারে CH3 single bond CH3 plus C2H5 single bond C2H5, or it can also form CH3 single bond C2H5 plus 2NaBr. Clear? This is the thing that you have to remember. And the next question is based on this format only, where there are two different alkyl groups, so there will be two different products. Now when you are writing the final answer, then as I have already told you, carbon needs to be balanced. But when you are trying to formulate your answer, you can omit also. Okay, 1 iodo 2 methyl propane. So it's a 1 iodo. So let us write CH2. 1 iodo means this one. 2 methyl is also right. 1 iodo 2 methyl. So 2 hands Wolfine and CH3. This is the first case. And second one is 2 iodopropane. Second one is 2 iodopropane. So CH3 C H I CH3. This is the thing that is being formed. Now you tell me what happens in a Woods reaction is this part. From this part the Cherakhani happens. Right? Cherakhani happens from that part. I part only Cherakhani will happen. So one thing can happen is both are getting attached from the eye center. One can happen, one is attaching from the eye center. First thing can happen, same compound getting attached from that eye center, and one can happen this eye center and that eye center is getting attached. So three possibilities are there. So let us write the possibility. Very simple question only. Suppose I am writing CH2 CH3. I am writing this compound and I am attaching this compound from this end. A little bit below. So this compound if I am attaching, then I should write CH, and to this is attached CH3. So I shall write CH3, and another CH3 is not attached to this. I will write like this. This is one compound that can be formed. Name depends on you. What is the name? Name writing is your job. Next, this is the different one. This is the R dash mixture. Now same compound if I am going to form, that's not very difficult to do that. Acha, here is version methyl. I missed out. CH3 and the same compound I am going to form, so that will be also having the same thing. Put here. Clear? And the third structure that can be formed is CH3 CH3 Done. These are the three possible structures. Now apply the longest chain rule and find out whatever is the name. Clear? Name finding is your job. Let me write it out over here. Comment IUPAC name. Comment the IUPAC name, because that is not my job to write. You have to practice something. Before the exam, if I say everything, that's not possible. The main things I have told you. There are simple things which you can do it on your own. No, just calculate by using the longest chain rule. Very simple. What is the difficulty in that? Longest chain rule is 1, 2, 3, 4, 5. 5 is there and 2 methyls are there. So 1, 2, 3, 4. 2, comma 4 dimethyl it will be 2, comma 2 dimethyl pentane. First one is 2, comma 4 dimethyl pentane. Second one is 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. 2, comma 5 dimethyl hexane. And last one is 2, comma 3 dimethyl butane. It is there. Nothing is there. Even I could answer it within that. Okay. Comment IUPAC then. Already I have found out the answer only. Then what is the use of your commenting? I have already got the answer. So let's write it down only. This is going to be 2, comma 3 dimethyl 2, comma 3 dimethyl butane. Check it out. Okay. 1 now 1, 2, 3, 4. 2, comma 3. Done. 1, 2, 3. This one is going to be 2, comma 5 dimethyl hexane. 2, comma 5 dimethyl hexane. Longest chain 1, 2, 3, 4, 5, 6. 5 and 2. And this one is going to be 2, comma 4 dimethyl pentane. Right? This structure hydrogen should be shown, because without hydrogen you will not get marks. Acha, clear with alkene or not? This was the alkene question, by the way. Clear with this? Done. So we are done with another set of thing, that is we are done with alkenes. What is our next topic? Next topic we have is our alkynes. What we have to study in this chapter? We have to study alkane, alkene, alkyne and benzene. Benzene will be the last topic. So we have completed with alkenes. I hope alkenes we have understood completely. You have understood alkenes, and you are now ready to enter into a new world. That's the world of alkynes. So let's begin with alkynes with the basic formalities that we have done for alkanes and alkenes as well. So alkynes. What do you know about alkyne? Basic property of alkyne. What is alkyne? A triple bond containing compound is alkyne, right? So first thing is it has a triple bond in it. So triple bond containing compound is alkyne. The basic formula or the general formula of alkene is alkyne, sorry, CnH2 and minus 2. These are the things that you already know, that you have done in class 10, right? And who is the first member of alkyne group? It's ethyne is the first member, right? Methane does not exist, so ethyne is the first member of this homologous series. There are a few small, just basic things about alkyne which you have learned in class 10 also. Now let us move on to the main thing, that is the methods of preparation of alkene. Come here. Preparation of alkynes. First from 1, 2 dibromoethane, and second one from 1, 1, 2, 2, tetrabromopropane. So from 1, 2 dibromoethane, how will you prepare alkyne? You already know that. How does it look like? This looks like, let me use a different color. 1, 2 bromoethane looks like CH2 CH2 Br Br. This is all about 1, 2 dibromoethane. Well, it's 2. Done. So from here I will be using what? What should I use to prepare alkyne? Tell me. What will I use to prepare alkyne? I will use alcoholic KOH. Clear? So if I use alcoholic KOH, what will I get? CH2. Clear? CH plus KBr plus water. Done. Understood? Understood? So we are going to prepare alkyne from 1, 2 dibromethane by this reaction. No doubt, I guess it's very easy reaction as well. Next, 1, 1, 2, 2 tetrabromopropane. It's a very important one. This was formed by the reaction of alkyne with benzene. Alkyne with bromine. Okay. So how does it look like? 1, 1, 1, 2, 2 dibromopropane. How does it look like? Propane is CH3, CH2, CH3. But here, so this side also 2 bromine, this side also 2 bromine. So it will be CHBr, CHBr, CH2, CH, oh no, not CH2, CBr, Br CH3. This is 1 comma 1 comma 2 comma 2 tetrabromopropan done. Now if I use alcoholic KOH, how many? 2 moles of alcoholic KOH. Because 1 mole won't work. 1 mole will form it alkyne. Alkene, not alkyne. So 2 times alcoholic KOH. Okay, that I have to write 2 times. Why? Because 2 molecules have to remove. Otherwise it will not form alkyne. So this will form CH3 double bond CH3. Clear? This will not propene. This will not from acetylene. This will from propene. Propine. Clear? So this forms propine. That understood? So I am taking 2 moles of alcoholic KOH. So what exactly happens? Alcoholic KOH, you know. Alcoholic KOH elimination reaction. I have taught you in the GOC lecture elimination reaction. So Br will be removed and adjacent hydrogen one it will be removed from here similar this Br and one hydrogen from here. So ultimately this will from elimination reaction. I have told you here also one Br removed, one hydrogen removed from Br removed, bond formed, Br removed, Br removed. Here bond formed. Here hydrogen is not available, so here bond will be formed in between. Clear? Understood? Here hydrogen not possible to remove. Here only both will be removed, bond formed. Both will be removed, bond formed. Done. Clear? So preparation of alkyne from 1, 1, 2, tetrabromopropane and 1, 2 dibromethane. Clear? Both were in class 10. Okay. Next what we have. Okay. Directly we are going to chemical properties of alkenes. We have done preparation. We will be reading only 2. Right now we will be reading only 2. Later on we will be reading. Okay. Now coming to chemical properties of alkene. Hydrogenation. Now see hydrogenation though we have already discussed for what? We have already discussed for the previous case, that is alkene. There we have seen addition of hydrogen results in directly formation to till alkane will form. It will till form alkane. So here we are going to see that it will form till alkane. Clear? But if we are using which catalyst? Lindlar catalyst, then the reaction stops at alkene part. Okay. Before I move on to this, remember that instead of 2 alcoholic KOH, if I use something else, I can also use another product. Let me use that only because alcoholic KOH is used above. So we can use, instead of alcoholic KOH, better to use zinc coupling with an alcohol. So this will end up forming ZnBr2. This is called reduction using zinc coupling. Clear? Zinc alcohol couple. Done. Okay, hydrogenation. So what is hydrogenation? Everyone knows. I need not tell you about hydrogenation anymore. So let me quickly write the reaction. CH triple bond CH in presence of nickel H2. Heat gives you CH2 double bond CH2, which does not stop here, which continues the reaction at nickel H2 heat CH3. Done. So remembering thing is reaction will not stop at alkene. It will go till alkane and it will stop at alkane. Okay. Next come addition of halogens. Just like we have seen addition of halogens in case of alkene. Similarly, the addition of halogen is also seen, but this is not going to be distinguishing test because both are same. For alkene and alkyne, how will you differentiate? That I will be telling you. But this is not a differentiating test. Okay. So when you add up, let us take, we are suppose have CH triple bond CH. Properly now, what is this? We have CH triple bond CH and we are putting Br2 CCl4 and we will see what? First step, bond will break, right? One bond will break. So CH double bond CH Br and Br. And again the reaction will continue because one more bond can be broken. So it will ultimately form CH double bond CH single bond CH Br 1, 2, 1, 1, 2, 2, tetrabromoethane. Clear or not clear? So this is going to be the final product form. What is the IUPAC name? 1, 1, 2, 2 tetrabromo tetrabromo. Clear? So this is addition of halogen. Very simple one. 2 step it will occur. There it was only 1 step occurring. Here also it will be occurring in 2 steps. Clear? Next, what do we have? Addition of halogen acids. So addition of halogen acids means HBr, HCl, HI all this. Okay, HI we generally don't use, but still. How will you add hydrogen acids? Following Markovnikov's rule. So it is CH triple bond CH and you add HBr. What will happen? You will write CHBr double bonded with CH2. Right or wrong? This way. This reaction will not stop over here because again another bond can be broken. So HBr, CHBr, Br, single bond CH3. Clear? This is addition of halogen acids using Markovnikov's rule. Now, if this is not a symmetrical alkane, symmetrical alkyne, then what will happen? Follow Markovnikov rule, already told. So, suppose it is CH3, C triple bond CH. Then, in presence of HBr, it will form CHC, C, Br, double bonded CH2, passed again with HBr to form CH3, C, Br, Br, single one CH3. Clear? Following Markovnikov rule. Done? Now anti-Markovnikov rule can also be followed. If I give H2O2 in presence of that HBr, then just ulta of whatever is happening, uska ulta. Clear? Anti-Markovnikov rule happening in H2O2 presence is anti-Markovnikov rule. Clear? So I am writing here. If H2O2 mentioned as catalyst, follow anti-Markovnikov rule. Follow anti-Markovnikov rule. Clear? So if there is H2O2, you find H2O2 is mentioned as catalyst, then do not use that as Markovnikov rule. Follow anti-Markovnikov rule in that case. Clear? Only when H2O2 is mentioned. Here no H2O2, so don't follow. Now, as a catalyst, another twist is also there. If HCl H2O2 I give, then it will not follow anti-Markovnikov rule. Then what is the condition I missed out? H2O2 mentioned as catalyst along with HBr. Mention that catalyst with HBr. This with HBr is very important because intentionally they will give HCl and H2O2. No reaction. No reaction means anti-Markovnikov will not occur. I'm sorry. Anti-Markovnikov rule will not be followed. Markovnikov will not be followed. Only HBr gives the anti-Markovnikov rule. That is Kharas effect. Only HBr gives in presence of H2O2. No other. Clear? Please remember this thing. Otherwise we'll forget. Next is hydration reaction. Hydration reaction is nothing but addition of water. Addition of water. Done. So how will water add? I already told in last class. CH triple bond CH. Here to add water, no. We will use another compound known as, at the last time what did we use to add water? H2SO4. I told you H2SO4 is a very good proton donor, so we will use H2SO4. Here along with H2O we will use Hg2 plus. Generally we'll find for alkynes we use Hg2 plus. So it can be given in a way concentrated sulfuric acid divided by concentrated, not divided by, I mean on the down side of the arrow, like this way. Suppose I said 20% concentrated H2SO4 and 1% HgSO4. This type of things can be given. What does this mean? H2SO4 is a proton donor and Hg2 plus will be helping in the mechanism. Here ultimately nothing will happen. The same thing what we are doing, it will also happen. It will only happen. Clear? So I will not write that complex thing. H2O, H plus in presence of Hg2 plus. What it will form? Water will be added. So CH2 double bond CHOH. Again the same reaction can occur. H2OH plus in presence of Hg2 plus, or one thing you can do directly tautomerism from there. You can do tautomerism or you can further take one and do it. No problem is there. Same answer will come. So I can write CH3 single bond CH upper OH niche OH. Now if you remember, I have told you in the last case only. Wait, let me show it to you. This one. Geminal diol does not exist. That means on same carbon two hydroxy groups cannot be there, right? I have told you that geminal diol does not exist. So if geminal diol does not exist, then this thing cannot happen, that there are two hydroxyl in one carbon. No. Then what will happen? Then nothing but this will go out. It will move out that water. So what will be formed is CH3, CH3, C double bond O, CH3. This also equal to tautomerism and directly come till here. If you want to do tautomerism and come here, no problem. Otherwise, you will be doing it in this way. Clear? So water will move out. Go. Water will go out as H2 minus H2. Tell me, understood or understood? It will undergo tautomerism. There only directly you can see, no, OH and double bond is there. It will undergo tautomerism and it will form ketone. It will form what? Ketone. Okay, understood this? So this is hydration reaction in case of alkyne. So you can see the reagent has Hg2 plus. So any compound of Hg which has Hg2 plus oxidation state can be given in the question paper, and instead of H plus I can give H2SO4. So please remember that if the reagent is given as H2SO4 by HgSO4, do not get confused. That is nothing but hydration reaction only. Same thing will happen over there. So I am writing it over here. Concentrated H2SO4 plus concentrated HgSO4 plus HgSO4 can also be given, can also be written. Okay. So if it is written, and don't think that what is it we have to not done in or not in our syllabus. No. Anything, any compound of mercury having mercury plus 2 oxidation state can be used over here, and concentrated H2SO4 is definitely a proton donor, so it will be used over here. Clear? Done. Next we have what? Addition of hydrogen cyanide. To add hydrogen cyanide, we have a specific reagent. What reagent we have? BaCN2. BaCN2, and obviously HCN we are going to add, we will be putting. So if we put this, then what happens is bond breaks, one side hydrogen goes and other side CN goes, like this. Clear? We have to use specific, at least barium cyanide. So BaCN2 done. Then this reaction happens, CH2, one side bond breaking, hydrogen enters one side and CN enters one side, symmetrical alkane, no problem is there. Then what happens? Then we treat this with H2O and H2. What are we doing? Hydrolysis. When we conduct hydrolysis of this thing, H2H plus is hydrolysis. Hopefully you all know that. Hydrolysis. We are doing hydrolysis, then what happens is this Cn minus goes. Gone. Okay, you tell me, if we are doing hydrolysis of this, on doing hydrolysis of this, we get CH2 double bond CH C double OH. Please remember that cyanides can be hydrolyzed to carboxylic acid, and what goes out as ammonia. Okay, ammonia goes out, and this is the product that is formed. Clear? Please remember, this is a very important one. Barium cyanide, when forming a cyanide when we conduct hydrolysis, carboxylic acid is formed and ammonia goes out. Clear? This is coming from the mechanism, not from here. Clear? For now, please remember. Okay, now coming to oxidation. The next stage is oxidation. We have two different type of oxidation. You all know that already. Number one, using Bayer reagent. Number one, using Bayer reagent. Bayer reagent. So CH3, let's take C, triple bond C, H, in presence of cold alkaline dilute KMnO4. That is there is a Bayer reagent, right? Cold alkaline dilute KMnO4. And what will be formed? To know what will be formed, you have to first know few things. What is that few things? That is right over here. Just like previously I told you that double bond CH2 gets oxidized to CO2 water, double bond CRH gets oxidized to aldehyde. This thing I have told you. Here also something like that is there. If there is triple bond CH, then oxidized to CH, triple bond CH is oxidized to RCOH. Sorry, triple bond CH is oxidized to CO2 water. And if there is triple bond Cr, then that is oxidized to RCOH. Alright. So here can you see this part? This part is visible? No. So gone. Other part is also visible, Cr. So you can see one side is visible CH, one side is visible Cr. So what will be formed? CH2COH. But only though this is also not possible. One side it will be this CH2C part will form ketone, while CH part forms a carboxylic acid. Clear? Now you say, you to wrote this thing, then why you are saying that thing I wrote because I will need it later on, not for this case. Okay, this is not for this case. If you are getting confused, then let me better erase it only. Let me erase it. And Shanti, this is not for this case. For hot KMnO4. Okay, CH3C triple bond H. If you are giving cold dilute KMnO4, then you will find what is this? Then you will find this part transforms into a ketone part. Okay, in presence of cold alkaline dilute KMnO4 only. CH3C triple bond or RC triple bond. Clear? And this part is transforming into COH group. And there is CH double bond. So what will you form? Tell me. One part is getting converted to ketone. So what I will write, CH3C double bonded O, ketone done. Then I have carboxylic acid, this one. So this is the oxidized product. Okay, clear? Now second one is, page কোথায় গেল? Just a minute. Number 2 is number 2, hot concentrated KMnO4. Hot concentrated KMnO4. Here you need to remember, this thing. Clear? Triple bond C oxidized to CO2H2O. Not in this case. Not in this case. Even I made that mistake, but it's not that case. In case of cold dilute alcoholic KOH, in case of cold dilute alkaline KMnO4, you will be using that case, and this case is different. Clear? So here, suppose let us take, we are taking example CH3, CH3, C triple bonded C CH3, and I am using hot concentrated KMnO4. Hot concentrated KMnO4. What am I supposed to get? Tell me. What am I supposed to get? This side I can see RC. So RC by C, what will I get? This side will become RC, so this will become COH. And this side also I can see RC, so this side will also become RC. Right? Both the side is RC, so what will be the product? CH3COH plus CH3COH. Understood? As easy as that. Done. But if I use the same product over here, same reactant over here, what was the reactant? Leave same reactant, not needed. Okay, clear? Any doubt? No, that will become long, not needed. Understood? Done. So I'm getting CH3COH, I'm getting CH3COH. Okay, here let us take another reaction because I don't think you have understood. So suppose I have acetylene and I am using cold alkaline dilute KMnO4. What is going to be formed? see, this part is getting oxidized to carboxylic acid. This part is also getting oxidized to carboxylic to 2 carboxylic acid. So it will be an oxalic acid. Clear? Simple one. Simple, simple. And here, ulta. That you have to remember which case what is getting oxidized. That is the thing you remember from this. Clear? Next topic. Ozonolysis. Now, ozonolysis in alkene, I have explained you what is ozonolysis. So, the same ozonolysis is also over here. So, not going into details, just telling you one example where you can understand what is exactly happening. Suppose I have acetylene and I am treating. First step is O3, second step is zinc water. If in the question it is mentioned on the arrow 1, 2, then directly we write the final product, right? So what did I tell you? You have to form a body. So body will be formed like this. Now, let me go back to alkenes ozonolysis and let me show you one important thing that is not here. Here. See, what I have told you that when you are breaking this, bond, this bond should not be here. There should be no bond over here, right? I have told you that there should be no bond between this two over here. In this body, there should be no bond in between these two, right? There should be no division of that. Because double bond completely breaks in ozonolysis. There is no remaining of any bond. But that will not be in case of alkyne. Understood? That is the primary difference. Here 3 bonds are there. So one bond will stay. One bond will be staying. So that means this will be existing. Then you prepare a body. No problem in that. But do not forget to give this bond in between. Because in case of alkyne, the bond does not break. 2 bonds broken, done. One still remaining. That one will still remain. Clear? So this is the body. And when I am going to give it with zinc and water, then what it will form is body breaks from which part? This part and this part. So this part will be HCHO. Wait. HCHO plus HCHO. Wait. HCHO plus HCHO. This should have been if there were no bond in between না এইভাবে হয়ে যেত বা কোনো অসুবিধাই নেই but here to HCHO the second hydrogen not there only how will I write HCHO then this product is definitely not correct and moreover there is a single bond in between what should be the correct product just see and write no you can see what is written H C double bond O here H C double bond O single bonded with another C double bond O this type of thing is formed clear plus H2 H2O2 then as simple as this is ozonolysis just you have to remember that in case of third triple bond one bond remains in case of alkene no bond remains because ozonolysis breaks 2 bonds done over that's all about ozonolysis simple polymerization what does it mean many alkynes combine to form a larger compound polymer okay that is called a polymer and this alkynes is called monomer clear what is formed is polymer who is combining is monomer so polymerization reaction is simply understand now in case of ethyne there was also polymerization but did not say it because it was not really important in that case that will form polyethylene as simple polymerization of acetylene is very important because it forms benzene so what will I take I will take 3 CH triple bonded CH and if I pass it through red hot iron tube then I will get benzene did you understand how what will get benzene now 3 CH means 6 so now I have no way to direct benzene clear or not clear clear this is simple and it is very important reaction because this generally comes for convert from acetylene to benzene directly from red hot iron tube if you keep it will get converted to benzene clear this is polymerization so CH triple bond CH they are coming together and they are polymerizing to form benzene every alternate bond break that is by one double bond one triple bond one double bond one single bond that's why it is there okay polymerization understood clear understood polymerization understood this ends our alkyne part. So we have covered three major topics of this chapter in a very short and crisp way. We have covered alkanes, alkenes and alkynes. Our next small topic is aromaticity. Then we will go for benzene, and that will be the last topic of the chapter. Let's come to aromaticity. Aroma, what is an aroma? Aroma is something which you can smell, a very good smell. So aromaticity is a special property of the organic compounds, not all organic compounds, but of conjugated cycloalkenes. Cyclo and conjugated means one after the other, one alternate, clear, which enhances the stability of molecule. Aromatic compounds are highly stable due to the delocalization of the electrons. Clear? So what points you need to remember? From here you need to remember the point conjugated cycloalkene. Conjugated means every alternate position. Alternate. Okay, alternate position double bonds will be present and they are highly stable. Why? Due to delocalization. Entire ring it is delocalized. Entire ring the electrons are delocalized. So that is why it will be stable. Resonance. You can understand that? Pi orbitals. Clear? So stability and delocalization of electrons present in the pi orbital. Entire delocalization will happen. Not like entire ring complete delocalization will occur. Then it is aromaticity. Definition not required. Just know it. There is a property of the conjugated cycloalkenes to increase the stability of that due to complete delocalization of pi electrons. Clear? Now let's come to the point. What we need to know, how will we know that whether one compound is aromatic or not aromatic? So that will be said by Haeckel's rule of aromaticity. Haeckel's rule. Haeckel's rule of aromaticity. Haeckel's rule of aromaticity. So according to Haeckel rules of aromaticity, we have three set of rules which we are going to take into consideration. Achha, first try to understand. If there is entire delocalization of electrons in the ring, then the ring has to be a planar one. Otherwise, it is not possible for complete delocalization. Clear? The ring has to be in one plane so that entirely it is delocalized. Clear? So Haeckel rule says, first point, the ring must be planar. The ring must be planar. So if the ring must be planar means what? That sp2 hybridized carbons must be present. sp2 hybridized. sp2 hybridized. Clear? sp2 hybridized carbon must be present. So ring must be planar. Number 2, complete delocalization should be there. Complete delocalization of electron. It's not like half-heartedly it will delocalize. No, complete delocalization of electron if it is there, then only it is Haeckel rule. Otherwise, it will not be aromatic. Okay, ring must be planar. Complete delocalization of electron should be there in the ring. Otherwise, this is not going to be aromatic. Simple, right? Complete delocalization. Number 3 and the most important one is 4n plus 2 pi electrons will be there. Pi electrons should be present. Should be present. Should be present. This is the most important one because actually this rule will differentiate. This is very important. Very important. 4n plus 2 pi electron should be present. Clear? So we have to count the number of pi electrons. Okay. Now let us, this much only for Haeckel rule of aromaticity. Just let us take up some example and I will leave you. Benzene, your favorite. How many pi electron does benzene have? Benzene looks like this. So how many pi electron? 4n plus 2, does it follow? 1, 2, 3, 4, 5, 6. So it is possible. 4n plus 2 can be 6. 4 into 1. So where n equals to 1. So this is an aromatic compound. So benzene is an aromatic compound. Nice. Now if I make two benzenes, then this is called naphthalene. Then how many turn? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 9, 10 is also 4n plus 2. equal to 10. This is also true for n equals to 2. So this is also aromatic. Right, now if I make, now if I give you a square and 1 electron, then 4n plus 4n, then how many pi electron? 4 pi electron. 4 pi electron does not fit in this condition, but it is anti-aromatic. Clear? Anti-aromatic. It is not non-aromatic, it is anti-aromatic. Okay, what is anti-aromatic? If 4n number of pi electrons are present, it is anti-aromatic, which is highly unstable. This is why anti-aromatics are very badly stable. Non-aromatics are still stabler than these anti-aromatic ones. Okay, this is highly unstable. So please remember, because chalaki kore question dite pare, 4n pi electrons will be anti-aromatic. 4n plus 2 number of pi electrons is going to be aromatic, and if it does not satisfy both the condition, it is non-aromatic. Clear or not clear? You have to remember that 4n plus 2 pi electron will be the prime rule for Haeckel rule of aromaticity. Done? Clear? Any doubts? No doubts. I think it's easy one, na? Okay. What we have next? Next topic is benzene. Next topic is benzene. Next topic is the last topic of today, benzene. So what is benzene? Everyone knows what is benzene. A very good looking ring, right? Very good looking white ring. This is benzene. You will represent it this way, or you will represent it in this way, or by resonance benzene can also look like this. So all these are benzenes. Only molecular formula is C6H6. This is basic thing about benzene. So what we have to study from benzene? We have to study the chemical reactions, that is electrophilic substitution reaction, and that I will not discuss in this lecture because it has already been discussed in the GOC lecture. Then we have to study about the preparation of benzene. That's all we have to study from this benzene. Okay. Okay. So let's start. The first topic we have decarboxylation of benzene. So how can I prepare benzene by decarboxylation? You have already done it in Wood's decarboxylation reaction. So first you are going to take a benzoic acid. This thing is called benzoic acid. I hope everyone knows. This also I have told you in GOC lecture what is what. So benzoic acid, I am treating it with NaOH. So water will move out, minus water I have written, and CONA is going to form. Done. Now this I am going to do decarboxylation. So NaOH in presence of CO minus Na2CO3, that is going to give me benzene. So this is my required thing, right? Decarboxylation reaction, understood? No doubt, I hope. Very easy ones. This is just have to memorize the reactions. Understand the reaction and memorize. Done. Okay. Now comes a phenol. What is phenol? Phenol is benzene with a OH, right? So what people do is just react it with water and gone. No, with water it will not react also. And if you add water to benzene, that will not add that water like that, because it is electrophilic substitution, not nucleophilic substitution. Clear? So what you have to do is you have to put it into zinc dust and heat it. It is actually distillation. Zinc dust distillation. If you do this, then you are going to get benzene minus ZNO. Zinc dust distillation of phenol will give you benzene. Not directly just add water or anything like that. No. Clear? Or you give alcoholic QH or gone suddenly. No, it will not happen also. Double bond will form on your head, it will form. Clear? Next we have benzene sulfonic acid. Benzene sulfonic acid looks what? Benzene. What is benzene sulfonic acid? Benzene sulfonic acid is SO3H. Done. So when you react that with water, when you react this with water in presence of HCl and heat it, then you get benzene. And what goes out is H2SO4. Clear? So from benzene sulfonic acid, you have to react it with H2HCl, then you will get benzene and H2SO4 go down. Then comes benzene diazonium chloride. Then comes benzene diazonium chloride. This diazonium chloride in class 12 we will need a lot. Benzene diazonium chloride. How does it look like? Benzene, on its head you have N2 plus Cl minus. This is benzene diazonium chloride. Where you have get N2 plus and Cl minus. From benzene diazonium chloride, if you are treating it with an alcohol, then what you will get is a benzene plus you will get an aldehyde, plus you will get N2 gas also, plus you will get HCl gas also. The Cl is also there. So many products you are getting. This oxidized to aldehyde, this N2 going out as N2, this HCl forming HCl. Done. It's a very simple thing, but you might find it very complex as well. Okay, this is benzene diazonium fluoride, and this is all you need to read from benzene. These are the preparation methods of benzene from different sources. Another source is also is called acetylene. The last source, acetylene. This I have already shown you. Still I am showing you again. 3CHCH in presence of red hot iron tube. No, sorry. Okay, clear. Another one is also there that I have not mentioned over here. That is from hexane, from alkane, from hexane. That is through polymerization reaction. Remember, from hexane polymerization reaction happens through polymerization of hexane. CH3, CH2, 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 CH3. Polymerization of hexane. Cr2O3, Al2O3, heat, benzene, plus 4H2. Right? So these are the things you need to remember. Chemical properties of benzene have been discussed in GOC lecture, so no need to repeat it. None. Next and the last topic we'll be discussing the directive influence of substituents. Now you tell me, what type of reactions do benzene undergo? Nucleophilic substitution, nucleophilic addition, whatever. What does it undergo? Electrophilic substitution. So benzene only undergoes electrophilic substitution. It does not do anything else. Nucleophile it will not touch also. So where does an electrophile love to get attached to? Where there is a electron rich center. Because electrophile itself is a vicary. So it needs to get attached to that position where there is too much taka, right? So that means that there is too much electron, then it will go and attach itself. It will attach to the electron rich center. So what is needed for electron rich center? Electron density will be transferred to the ring, or electron density will not be transferred to the ring. Obviously, it will be more reactive when electron density is transferred to the ring, and that position will attach. If there is such a substituent which is having minus m effect, pulling away the electron density from the ring, then it will not attach very much to that position, right? So this is the concept basically that you have to use. Now before I move on to that, let me say you chlorine, bromine, the halogen one, these are highly minus I have told you. These are highly minus I. No matter wherever they are putting inside the benzene ring, they might donate electron. If you put it in chlorobenzene, if you make, then chlorine has a lone pair, it will keep on doing plus m. But that plus m also is there, but their minus I is more than the plus m. So they are giving electron density to the ring, but they are pulling more electron density to the ring. So where will the electrophile attach? The electrophile will attach to that position where the electron density is not coming. Okay, that is the meta position. So let's understand what is reactive influence of substituents and their effect on reactivity. Suppose I have a substituent, let us take nitrobenzene. What I have? Nitrobenzene. Nitrobenzene. How does the nitrobenzene look like? N double O plus O minus nitrobenzene. Now you know that nitrobenzene can resonance. Nitrobenzene can do resonance. Nitrobenzene will do, nitrogen has two lone pair. Sorry. Nitrobenzene can do resonance, and what will nitrobenzene do? Turn mere toolway, right? This nitrobenzene can turn mere electron, it will be pulling the electron towards itself. Right or wrong? Correct. This is actually a coordinate bond, no? For this will form this way. Coordinate bond is being formed. Right, the coordinate bond is there. So this minus won't be there right now. It will come a little bit later on. Clear? What will happen? Nitrogen, this bond gone. Nitrogen pull electron towards itself. So double bond N O minus, coordinate bond with O plus. Done. So what happens? This central I cannot give anymore because now the bond has been broken. That one bond will break. So what will happen? Let me draw a better benzene because I cannot be able to explain it to you like this. Clear? This, there was a bond over here, right? That bond gone away. So there will be a plus charge over here, like this. Similarly, resonance will occur. Resonance we have all done now. Then what will happen? Plus will come here, bond will form here, NO, whatever it is there, sorry, like this, right? Similarly, one time the plus will also come here, the plus will also come here, N double O, no, not double O, sorry, N single O minus O plus, right? So you can see this plus charge comes at ortho position, meta position does not come, para position, again ortho position. So you all know ortho, meta, para position, right? I think I have told you in the GOC lecture only. If I have not told you, then I am telling you now. Ortho, para position with respect to these two, these are the ortho positions. Clear? These are the ortho position. Ortho. This with respect to this, with respect to this, these two are the ortho position. With respect to that only, if I show this, with respect to this position and this position are meta position. These two are meta position. Okay, and with respect to this, this position is para position. Clear? With respect to this position is para position. So please, ortho, meta, para you have to remember now, because many a times you will need it. Ortho, para, meta. Clear? Ortho is plus 1, 2 position, this is 1, 3 position, that is 1, 4 position. So plus charge comes in ortho position, plus charge comes in para position, meta position, plus charge does not come. So tell me, where will the electrophile attach? Where there is electron deficient center, electron rich center. So where is electron rich center? So where will the substituent come and attack? Meta position. So this is meta directing activating group. So you know, therefore, let me write it as electron density is less in para and ortho position. Electron density is less in ortho para position but high in meta position. Therefore electrophile will attack. Electrophile attacks, attaches at the meta position. Clear? Now NO2 is doing what? Pulling the electron or giving electron density to a ring? Taking the electron density. So that is a deactivating group. Clear? Next you will write, since NO2 shows minus M effect, that is pulls away electron density from ring. Therefore it is deactivating group. Therefore it is meta directed deactivating group. Meta directed deactivating group. This line is very, very important. Meta directing deactivating group, because question will be asking for what is meant by meta directed deactivating group. Example you will give and give examples of meta directed deactivating group. So meta directed deactivating group understood. Why it is meta directed deactivating group? Deactivating group because minus M effect. Meta directed because electron density is high at meta position. You can see plus is on para and ortho. So that side too, definitely electrophile will not attack. Okay. So example of meta directed deactivating group. Meta directed deactivating group example, NO2, that we have already seen. Other than that you have OCH3, no, not OCH3, sorry, COCH3, CONH2, carboxylic COH, aldehyde. These are all meta directed deactivating group. Understood? Reactive influence of substituents on effect on the reactivity. Okay. Next we will be seeing the other case. What is the other case? Other case is with the deactivating group. There can be activated grouping, activating group as well, that we will see. But there is no such group which will be meta directed but activating, not possible. Meta directed activating group, not possible. But ortho para directed activating group, possible. Okay, let's come. Uh, page. Next, we are continuing with the activating group only. Now, let's check next one. Next one, suppose I am taking. Color change the code. Just a minute. Now, I am taking another compound. Let us take. This time I have taken aniline. What is this? Aniline. How does aniline do resonance? Aniline does resonance by plus M effect. This lone pair gets into the ring. So double bond NH2 plus. What happens? Lone pair comes into play. So bond breaks minus. Right? Then minus comes here. Bond forms here. NH2 plus. Second last resonance. Here, minus here. Right? I am bothered with the three step. Another last step is there that you show. I am not showing. Okay. Another step is there that you will show. Achha. Now you see, in this case, the electron density is very high at which position? Ortho para position. So where will the electrophile supposed to attack? Definitely at the ortho para position. You understand the logic? Logic is very simple. Very simple logic. That wherever the electron density will be high, the electron deficient center will be attacking there only, because they need electrons, so they will be attacking at the high electron centers. Clear? So this ortho para position, the electron center is high, meta position, the electron density is low. So this is going to be a ortho para directed activating group, because this is plus M effect. Clear? Here see, where did it go? Sorry. This was ortho para less electron density. Here ortho para is more electron density. So this will be ortho para directed activating group. This was to minus M effect. This is to plus M effect. Clear or not clear? So let us write that as electron density is low at meta position. As electron density is low at meta position but high in ortho and para position, comma, electrophile attaches at ortho and para position. Ortho and para position. Done. Now, since NH2 is a plus M effect group, right? That means it shows plus M effect. Therefore, it is a ortho para directed activating group. Ortho para directed activating group. Very, very important. Ortho para directed activating group. What does plus M effect group mean? Gives electron density to ring. So this is a ortho para directed activating group. Clear or not clear? Ortho para directed activating group. Now we need to know some example of ortho para directed activating group. So let's know other examples of this. If aniline comes, phenol will not come, is not possible. So NH2, OH, OCH3, these are all having lone pair. NH2 done. Then NH, C double bond O, C NH3, CONH2 actually. Clear? These are all ortho para directed activating group, because they all have lone pair and they can give electron density. Now tell me, clear or not clear? this part and this part. Clear or not clear? I am giving the reason for everything because this is very important for you all to know. Done? Clear? Now we'll be discussing about a special phenomenon. Okay, special case, it is a halogen case. Halogen case, halogens are highly minus I. They are even plus M is more than minus I. So in that case, the minus I is dominant over plus M. Here all plus M's are dominant over their I. NO2, OH, they are all minus I effect group, but they also have plus M. Their plus M is dominant on the minus I. But in case of halogens, their minus I is dominant over plus M. That is why they will be ortho-para directed but deactivating group. So let's see chlorobenzene. This is chlorobenzene. Chlorine has lone pair, so it can donate the lone pair. So if it is donating the lone pair, then what will happen? Minus, same thing, na? Double bond Cl plus minus double bond Cl plus minus double bond Cl plus. Done. Now you see electron density is high at this position, this position, this position, this position, but it cannot attach to that position. Now you will say, Arey, what is this? Electron density is high. Electron density is high, but that does not mean that the chlorine is not pulling electron. Chlorine has a dominant minus I. So where is the electron density low? Meta position. So that is not being much affected by the chlorine's pull of electrons. So that position still has a higher electron density than the position at orthometa or orthopara. Sorry. So that position it will attach to. Now you tell me, clear or not clear? It was supposed to be like chlorine is pulling electrons. Done. Chlorine is pulling electrons from the orthopara meta, whatever it is pulling. But if it is pulling from meta, meta is already having a low electron density and chlorine to aro tanche. মেটাতে ইলেকট্রন ডেন্সিটি তো কম আছে, মেটাতে ইলেকট্রন ডেন্সিটি নেই, প্রায় কম, আরো টেনে নিচ্ছে। সো হোয়াট উইল হ্যাপেন? উইল দ্য ইলেকট্রোফাইল কাম এন্ড গেট অ্যাটাচ টু মেটা পজিশন? একদমই অ্যাটাচ করবে না, বিকজ অলরেডি দেয়ার ইজ নো ইলেকট্রন ডেন্সিটি দেয়ার। তো ওয়্যার উইল দ্য মেটা পজিশন, সরি, তো মেটা পজিশন তো গন, no meta position. Where will the electrophile attach? Now wherever is a minus hydrogen electron density, so that position is known as the ortho and para position. So this is also going to attach to the ortho para position, but this is not activating group. Why? Because Cl is highly minus I, so it will be deactivating group. Clear? This is the main case where you have to remember. So this region is same as the previous region, so I am just copying up the region, not writing. Okay, this region I am just copying because same region as previous. Copy, paste. As electron density is low at meta position but high in ortho para position, it will attach at the ortho and para position. Done. But Cl is a highly minus I group, highly minus I group. Minus I dominant over minus I dominant over plus M. Hence, therefore hence oblique. Therefore, it becomes deactivating group. It becomes deactivating group. Okay, clear? So what will I write? It is therefore it is a ortho-para, it is an ortho-para directed deactivating group. Ortho-para directed deactivating. Very important. This space is very important. Ortho-para directed activating group and deactivating group. Meta directed, always deactivating groups are only at meta. Meta directed activating group you will not get. If it is meta directed deactivating. Clear? So example of this is only halogens. Okay, example halogens. Clear or not clear? Okay, so this was the end of our hydrocarbon. That is all about hydrocarbon you have in your exam. Okay, that's anything I have next? Questions? Yeah, I have next. So let us do some questions. What do you say? Let us do some questions. I have few questions, so let us do these questions. Let's start. Let's revise what we have learned. Ethane to butane. 2 carbon increase, no? Ethane is 2, butane is 2. 2 carbon, butane is 4. 2 carbon increase. So what we will use? Simply we will use Wood's reaction. But Wood's reaction we directly cannot use. Why? As I told you, you need halide, alkyl halide. So first I have to convert CH3 to CH3 CH2Cl. Convert it using Cl2H nu minus HCl. Done. This I will be performing dry ether 2 times dry ether to get CH3 CH2 minus 2 NaCl. Done. Butane got. Next, ethane to ethene. Ethane to ethene. Now here you see, you knew alkene to you can convert. Now how will you convert from an alkane to an alkene? That is also very easy. From alkane to an alkene. How will you convert alkane to alkene? How? You have to use alcoholic KOH. This case you have to use alcoholic KOH. Right? So what will I do? First I have to write ethane. CH3 use H nu and Cl2 minus HCl. So I will get CH3 CH2 Cl. Now I use alcoholic KOH. When I use alcoholic KOH, Cl will be taken up from this carbon and H from this carbon. This is called beta elimination. Told no, beta elimination. This is beta elimination. So this will form CH2 double bond CH2. Clear? And KCl will go out. KCl the how many? 1. I water 2. Done. Clear? This is ethane to it. Next, ethene to formaldehyde. Ethene to formaldehyde. Achha, from a alkene to an alkanol, that is to aldehyde. How do you go to aldehyde from an alkene? Only one way you have learned to go from alkene to aldehyde, that is by ozonolysis. Only ozonolysis can result in that product. So we have to conduct ozonolysis. So please conduct ozonolysis. CH2 double bond CH2. When you conduct ozonolysis, you have to write like this: O3 and number 2 Zn water. Ozonolysis you will conduct, then you will get HCHO 2 times, to 2 HCHO. Done. CH2 though. 2 times HCHO and another product minus H2O2. That's done. Clear? This much easy. Why do you think so much? This much is only. It's done. Next, number 4. What do we have? But2 to but2,3 diol. But2 to but2,3 diol. That's very simple only. Just add water on bias reagent. But2 is CH3 CH double bond 1 2 3 4 CH3. But 2 in here you have to write bias reagent: cold, alkaline, dilute, KMnO4. Then you will get CH3 CH OH CH OH CH3. Done. Next, ethanoic acid to ethanol. Ethanoic acid CH3 COOH. Ethanol LiAlH4 C2H5OH. This I might not have told you what to use. LiAlH4 is a reducing agent. Okay, so you have to use any such thing which will be actually going to reduce. So this is going to be a reducing agent. Whenever you have to reduce something, use LiAlH4. Okay, this is a reducing agent. So you have to use LiAlH4 to get directly to reduce it. Done. Acha, one mistake I have done. This will be one more step will be there. Okay, you are going to reduce this in the term of aldehyde. So this will get aldehyde first. Directly we cannot go, no? Aldehyde, then again LiAlH4, then to alcohol C2H5OH. Now, okay. Next step. Next, ethanol to ethanoic acid. Just now so we did something. Now just ulta. Now ulta, so what will you do? So we will use oxidizing agent. So we will use C2H5OH K2Cr2O7 heat. Or one thing you can do directly to carboxylic acid using hot concentrated chemical. That is also correct. If you use this, you will get CH3CHO. Acha, H plus as well. Yes, H plus. K2Cr2O7 slash H plus heat to get CH3COH. Understood? This is the way you have to do. Very easy things. You can understand. It's very easy now. Okay, next. How will you convert to ethyne to methane? A very important question. Very important question. First of all, you have to degrade the number of carbons. Somewhere you have to conduct decarboxylation. But how will you conduct decarboxylation? You have to conduct decarboxylation of sodium acetate. So I need to get till sodium acetate. What I can understand is I have to get till CH3CONA. Here if I get, then I can directly get methane. But till this step, for this I need something else. What do I need? What I need? Carboxylic acid. I need carboxylic acid. I need CH3COH. That I can get from methane. Yes, I can get from methane. How will I get it from methane? Just now I have told you. CH triple bond CH. If I react that with H2SO4 and HG2 plus, sorry, H plus H2SO4, HG2 plus, then what am I supposed to get? I am supposed to get CH3CHO. Right or not? This will form what? 2OH that will go out, ultimately forming one aldehyde. See here, CH double bond CH, OH, H, CH single bond CH3 and OH, OH. Two carbon same OH cannot be, so it will form CH like this. So this is what? CH3CH, it's only what I've written. Okay, this is just a mechanism. I just showed you the mechanism. Okay, how it is coming to CH3CHO. Done? Now CH3CHO, I can oxidize it by using K2Cr2O7 H plus. In presence of heat, I can get it to CH3CONA. Now, sorry, CH3COH. Now, NaOH I can treat it with to get CH3CONA. Now, decarboxylation to get methane minus Na2CO3. Tell, clear or not clear? Easy? H2. Easy? This is all. This question is also very interesting. Isopropyl bromide. Isopropyl bromide looks like this. This is isopropyl bromide. Done. Now I am treating it with alcoholic KOH. What will happen? Bromine will be removed and one hydrogen from either here or here it will be removed. So I can write this as this way. This way. When I am using HBr, and you can see I am using H2O2. HBr H2O2. Then what will happen? Anti-Markovnikov rule is supposed to happen. This side is least hydrogen, this side is more hydrogen. But what it will happen is it will attach to this side. Done. So A is this thing and B is that much easy is the answer. Clear? This much easy is chemistry. Chemistry is very easy. If you have to just understand what is happening and how it is happening. That's all done. Okay, now we have completed the chapter hydrocarbon. What I will do is now I will just tell you one last thing, that is the differentiating test between alkene and alkyne. That much I will tell and it's done. Okay. So do I have page? Yes, I have. Okay. Here I am going to say you about differentiating test. Differentiating test between alkene and alkyne. Bayer test or simply bromine CCl4 test, that is for unsaturation. Now in unsaturation also, whether it is alkene or alkyne, I have to have some test to differentiate between that also. So in that case we use a reagent. We use reagent ammoniacal cuprous chloride. Reagent ammoniacal cuprous chloride. Ammoniacal cuprous. Okay, remember the reagent because it's a very important reagent. Now how exactly things are happening, let's see. In case of ethylene, CH2 double bond CH2, and in case of acetylene it is, I'm giving a 2 gap between them, and acetylene it is CH triple bond CH. Line is not visible only. See the condition of the line. Line I cannot see only. Whether the line is existing or not, I cannot see. Now I can see the line. Okay. Now you see. This is ethylene is acetylene. Now, when I am reacting ethylene with ammoniacal cuprous chloride, suppose ammoniacal cuprous chloride, this one, okay, I'm not writing this huge name now. So what will happen? Nothing. Got the no reaction. Clear? No reaction will occur. But if I am having acetylene and if I give the same here, then some reaction will occur and this will be formed. And this is going to be at a red PPT. This is called copper acetylene. So what did you understand from here? Presence of acidic character is very important. Acidic character. Triple bonds are more acidic than double bonds. So acidity is over here. So acidic character is involved. Triple bond is more acidic. So presence of this acidic hydrogen is very important. Acidic hydrogen got replaced by copper, but here the acidity is less, so this acidic hydrogen cannot get replaced. Clear? So this is red PPT, there is no red PPT, and that is the differentiating test between both of them. Clear? Understood? So this hydrogen are acidic hydrogen. Acidic hydrogen. Because of acidic nature, this hydrogen attached to this is acidic hydrogen. Clear? Understood? Acha. Another one you will find, not very required, but sodamide reaction. Sodamide. Generally, we will find this is also acting as a reducing agent only. Just I am giving you no doubt. Like suppose CH3CH reaction with NaNH2. This is sodamide. All these are due to their acidic nature. So it will be like Na plus C minus triple bond C minus Na plus. This type of thing. Okay, NaNH2. But NaNH2 is actually a reducing agent. If it is given in alcohol medium, it will perform the same function that alcoholic KH does. But here, if I give only NaNH2, then Na will replace H, acidic hydrogen. It is again proof of acidic nature of alcohol, of alkyne. Clear? This is all that I have to say from this chapter. Please read the chapter carefully because this is very important. Why to waste one page to fit that? Wait 1 minute. So I have fixed this in one place. Clear? Sodamide is also might be asked in sometime between. If there is nothing is there, NaH2 will do simple this reaction, and if something else is asked, then it will do that particular reaction. Clear with this? This is all about. You have to study from hydrocarbon. I hope you have understood hydrocarbon, and exam is very near. So all the best for the exam. Let's see what question paper comes. Hopefully it will be an easy question paper. But whatever concept you have learned from there, that only will be asked in the exam. So you have to prepare accordingly. So that's all. That's the end of class 11 as well. So we'll begin with a new journey of class 12. So stay safe, take care. We'll see you in the next video.